that recent advancement in science and technology. Science, you know, it's an opportunity. It opens the floodgates of possibilities. And technology is just a facility. It facilitates us to know what we should do. And we want to use it to the advantage of human beings. If science does not do anything good for humankind, it is no science at all. We are here not for any fake science, not for any pseudoscience, but for genuine science. So that's why, you know, Ramakrishna Mission Vidyamandira of Belur Math, which has recently been declared as college with potential for excellence by NAC, has arranged this. They have organized it, and it has been sponsored by Ceramic Glass and Glass Industry Foundation, American Ceramic Society. Our program will be divided in 3 sections. One is inaugural session. In inaugural session, we are going to present before you Vedic chanting first. Our day begins with a bird song, but here in Asrama, whatever we do with a Vedic chant. Veda, you know, always encourages to have knowledge. So it is quite natural for us. Next will be welcome address and keynote addresses. In the first part, within 11:30 we will try to finish it. Next there will be technical session. 2 famous professors of our country will be here. They will deliver a talk on different areas of science which will help you. And they will present it with PowerPoint presentation. Obviously it will be in English, but I have requested them to tell also sometimes Bengali, bilingual language, so that you can be benefited by it. So in the first session, Professor Ashok K. Mullik will deliver a talk on maths and Ramanujan's maths in school standard. He will talk on it. Next, our Indranil Manna, both of them are IIT Kanpur professors. They will be here. Next, there will be a lunch break for 1 hour. And after the lunch break, we'll resume the second part of the session. Professor Vikram Basu, a very erudite scholar of Indian Institute of Science, Bangalore. He's already here. He will give a speech here. Next, there will be another one. Professor Tanushree Shah Dasgupta, Indian Association for Cultivation of Science of Calcutta. He is also here, and she will speak to you on nanotechnology and computational science. Next, Professor Rahul Banerjee is associated with Indian Institute of Science, Education and Research, Kolkata. And many of them, he is also one of them, Bhatnagar Award recipient. And the last one is Dr. Uttam Kumar Gorai of Ramakrishna Mission Vidyamandira Belur Math. He is the head of the department of our Vidyamandira. So, we are going to start it in that way, but before that, let me tell you that what science has given us the opportunity and how science has made us in a different way a very, very efficient persons in this world. You know that cavemen has now become a homo cosmonaut or a homo astronaut. But now we have excelled that stage, and now we are homo liquidator. That means a mind, a creature of mind. And you see how science is running, keeping in pace with these things. In decades, we think that BrainNet will augment the internet. Computers will disappear. Computers, as we now know them, will disappear. They will be everywhere and nowhere, ubiquitous yet hidden, just like electricity and running water. We can have computer in a very, very short time. Next is, you will see that internet positions in decades to come will control computer with our minds, not with a mouse, not with the clicking of a mouse. I will apply my brain and I can use computer. We are trying to do this. Next one is, suppose, that is very, very interesting part, aged people can replace their body parts like auto parts. The aging will be stopped. And already from your own cells, scientists can grow skin, cartilage, noses, blood vessels, bladders, and windpipes. In the future, scientists will grow more complex organs like livers and kidneys. The phrase organ failure will disappear. So these are the possibilities. With the hand of technology, we are getting that. And the aging process may be solved also. Our dignitaries are gradually coming. Please, Maharajas, take your seats. So, our program, the first one, we will start with Vedic chanting. I will request those who will participate, please come on the dais and start.
Gurubhyo Vidyamandira Tejasvinavaditamastu ma Vidvishavahai. Om Shanti 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 Harihi Om. Shangno Mitra Shang Varuna Shangno Bhavattaryama Shangno Indro Brihaspatihi Shangno Vishnurukramaha Namo Brahmane Namaste Vayo Tvameva Pratyaksham Brahmasi Tvameva Pratyaksham Brahma Vadishyami Ridam Vadishyami Satyam Vadishyami Tadmamavatu Tadvaktaramavatu Avatu Mam Avatu Bhaktaram. Om Shanti 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 Harihi Om. Bhadram Karnebhi Srinuyama Devaha Bhadram Pashyemakshavirjajatraha Srirairangai Stushtuvagyam Shastanubhihi Vaishema Deva Hidayadayu. Om Shanti 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 Harihi Om. Ridagam Satyam Param Brahma Purusham Krishna Pingalam Urdharetam Virupaksham Vishwarupaya Vai Namo Namaha. Om Shanti 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 Harihi Om. Purnamadah Purnamidam Purnat Purnamudachyate Purnasya Purnamadaya पूर्णमेवावशिष्यते। ॐ शान्ति शान्ति शान्तिः। हरिः ॐ तत्सत्। श्रीरामकृष्णार्पणमस्तु।
We pray to our Holy Mother and we also seek for her blessings. A very good morning to all of you who are present here, and also very good morning to the eminent scholar and honored guests and our beloved students. I take this privilege to welcome you all. First, I welcome and I also offer my Shashtanga Pranam to revered Vidyamandira Maharaj, who is the Secretary of Ramakrishna Mission Sarada Pit and also the Senior Trustee of Ramakrishna Math and Ramakrishna Mission. We get him amidst us in spite of his busy schedule. He has come over here and joined us. So we offer our respectful pranam on behalf of our Ramakrishna Mission Ashrama Narendrapur. Maharaj Pranam. In the dais, our revered Secretary Maharaj, Secretary of this Ramakrishna Mission Ashrama Narendrapur, Swami Sarvalokanandji is there. I offer our pranam. Sarvalokanandji is the host of this program and also the guardian of our ashrama. I offer my humble pranam to him. On the dais, revered Shastrughanandji Maharaj is there. Shastrughanandji is the principal of Ramakrishna Mission Vidyamandira College of Belur Math. Maharaj actually has taken the initiative for arranging this whole program or whole seminar. We offer our respectful pranam to him. On the dais, Ashok Mollik is there. Sri Ashok Mollik, he is actually the former professor IIT Kanpur, and he will deliver a talk on mathematics in the technical session. I offer our namaskar to him, and in the front of this hall we will find Professor Indranil Manna from IIT Kharagpur, as well as he was the former director of IIT Kanpur. We offer our respectful namaskar to him. And amongst us, Professor Bikramjit Basu is there. Bikramjit Basu, actually he has taken also the initiative for arranging this whole program, this whole workshop. The first day here at Narendrapur and the second day it will be held in the ashrama campuses of Sharada Pit in Vidyamandira College. Professor Basu, he has come from IISc Bangalore, Indian Institute of Science. So we offer our respectful namaskar, extend our gratitude to him. Professor Tanushree Dasgupta, Indian Association of Cultivation Science, Kolkata. She has come. She is also the S.N. Bose Chair Professor, Fellow, American Physical Society. She will also deliver a lecture to you. We also offer our respectful namaskar to her. Professor Rahul Banerjee, he will come here probably at 2 o'clock. Rahul Banerjee, also SS Bhatnagar awardee, and he is also working in ISAR, Indian Institute of Science, Education and Research, Kolkata. He will come here and he will deliver the lecture. So we also offer our respectful namaskar to him. He will be here. On this great occasion, our Professor Dr. Uttam Kumar Ghorai, who is the head Industrial Chemistry Department, Ramakrishna Mission Vidyamandira, he has taken this initiative with his full team, the departmental scholars with the boys, departmental students of his college. So we also offer our namaskar to him. In this hall, sannyasins are there, revered sannyasins. We offer our respectful pranam to them, and also brahmacharis Maharajas are there. So we offer our respectful namaskar to them. So many students have come over here, more about 200 students from different schools of Kolkata. If you have come over here, basically for you, we have arranged this workshop. So I welcome you on behalf of this Ramakrishna Mission Vidyalaya and Ramakrishna Mission Vidyamandira, Belur Math. If you have come over here, I think you will enjoy the whole day and you will get a perfect path of taking this and you will have this temper of this science. So I welcome you all, those teachers who have come, who are the escort teachers, with them who have come here. So I also offer namaskar to them. I think this whole day you will be busy with the science temperament and you will enjoy the whole seminar. So let us pray for this success of this whole seminar. I welcome you all who are present here. Namaskar.
The first one will be delivered by Swami Sarvalokananda, Secretary, Ramakrishna Mission Vidyalaya. Please, Maharaj, come up.
It is a proud privilege of Ramakrishna Mission Ashram Randrapur to host this prestigious national workshop. I must thank the authority of Ramakrishna Mission Vidyamandira, Belur, for having chosen this ashrama, this place, as a venue of the workshop. Dear friends, science and technology have made tremendous strides over the last few decades in different fields. In the field of medicine, nanotechnology, then computer science, then other different fields. All of you know that science has been able to perform mind-boggling feats which were incredible, say some 15 or 20 years back. An amazing discovery of science and technology has made our life or our human lifestyle more comfortable and sustainable. But so far, or whatever science have discovered is not enough. I can say it is very little, because the knowledge is like a vast ocean. All of you know. And the scientists, they have admitted and declared very rightly that we have been able to collect some pebbles lying on the seashore. That is why Sri Ramakrishna has rightly pointed out that Jabod Bachi Tabod Sikhi. As long as we live, so long we learn. Dear friends, we are ignorant, unaware about many things of this universe. For example, the innumerable cells in the human brain, which are called neurons. But unfortunately, the behavior, the functions of the neurons most of the neurons are not known to us. Therefore, there is no end of knowledge. There is no end of learning and knowing. The tendency of human mind, or the nature of human mind, is to know more and more. It cannot be satisfied with the little things. Human mind always inquire, search for more and more knowledge. There is no doubt about it. Dear friends, researches are going on, and the research of knowledge also is going on, because human being wants to know more and more about the mystery of the universe. Though science has not been able to unravel the mystery of the universe, the scientists are doing wonderful work in this line. And we are sure that the science will be able to know or unravel the mystery of this universe. Dear friends, I have to tell you, you must know the history. Rather, history, the ancient history of India. You will find that in the past, India was great in many fields. In the field of science and technology, in the field of literature, in the field of music, in the field of architecture. There are many fields India was great. There is no doubt about it. Perhaps the science students are sitting here. Perhaps you know that Indian scientists, I should say the spiritual scientists, they have discovered many things. And all of you know that no American or French scientist discovered the digit. It is our own scientist, the great scientist, Aryabhatta. He discovered the 0 digit. Most of you know that the aeroplane was discovered or invented by Wright brothers of America. The fact is not correct. You will be surprised to know that the design and plan of aeroplane was discovered or discussed by our great spiritual scientist. He is called a great spiritual scientist. That is a great spiritual searcher. He actually discovered Bharadwaj Muni. His name was Bharadwaj Muni. Actually, you will find that there are 1800 verses on the design and plan of the aeroplane. But most of us do not know it. Then, nearly 100 years ago, one of the Maharashtrian scientists, Purkare, he discovered the documents, the design and plan chalked out by Bharadwaj Muni. And he was very much successful in designing the small plane, and he could help to rise the plane up to the height of 20 feet, 200 feet. Then the British scientists, they came to know about the Purkare's achievement, and always you know these British are very clever. They went to Purkareji and requested him. He said, "You do not have so much of money to make design of a huge flight or carrier, so it is better to give these all documents to us. We'll make a huge carrier or flight." And this British scientist, they took this document to Wright brothers. In those days, the Wright brothers were doing research on huge carrier or flight. When Wright brothers got these documents helped them to make a huge carrier or flight. But unfortunately, you do not know that it was discovered in this land, the land of India. But everybody knows that Wright brothers discovered and invented aeroplane. There are so many things in the field of medicine. Now you find there is a lot of developments in medicine. I think this most advanced technology nowadays, the medicine. But in medicine you'll find that thousands of years ago, this medicine and surgery was discovered, rather discussed. This medicine and surgery by Charak and Susruta. They are great teachers. They are great physicians, surgeons. Because I was in the hospital, looking after the hospital, I know most of the surgical equipment nowadays are being used for operation. And those instruments are designed by Susruta, the great surgeon in those days. You know the Charak and Susruta Samhita. So dear friends, don't think that in India nothing was discovered, nothing was invented. And so many things the Britishers, they borrowed from India and they did research on it and they become successful. So dear friends, this process of learning is a huge. Not only that our scientists, they are doing research, they want to know more and more, and science has yet to go long way to know more and more and to discover more and more for human benefit or human welfare. Dear friends, I don't want to take much of your time. Most of us do not know the recent development, achievement of science and technology. And we are very fortunate that we have many eminent scientists with us today, and undoubtedly they will enrich our knowledge about the recent advancement or development of science and technology. All the way from Kharagpur, from Bangalore, our scientists have come and they will enlighten you about the recent advancement and development of science and technology. I think many young students, bubbling with energy, with a fresh mind, are sitting here. I would like to request you, please increase your inquisitiveness. যাকে বাংলায় বলে জানার আগ্রহ, জিজ্ঞাসা, সেই জিজ্ঞাসাটা বাড়াতে হবে। যখনই তোমার জিজ্ঞাসাটা বাড়াবে, I think you all know Bengali, quite comfortable in Bengali. যখনই তুমি এটা বাড়াবে, তোমরা বাড়াবে, অনেক কিছু বাড়াতে পারবে, অনেক কিছু জানতে পারবে, শুনতে পারবে। সেই জন্য জানার আগ্রহটা বাড়াতে হবে। এবং যারা এখানে বিজ্ঞানীরা এসেছেন, যারা আলোচনা করবেন, আশা করি তোমাদের সে জানার আগ্রহটা আরো বাড়িয়ে তুলবেন। এবং জানার আগ্রহটা বাড়িয়ে তোলা কিন্তু খুব দরকার আজকালকার দিনে। এবং এনারাই পারে, যারা টিচার্স, তারাই পারে কিন্তু জানার আগ্রহটা বাড়িয়ে দিতে। With these few words, I will conclude my short speech. And whenever I wrap up my speech, I end up with a famous Vedic prayer, that is Sarve Bhavantu Sukhina, Sarve Santu Niramaya. Let all be healthy, let all be happy. Namaskar, Dhanyavad.
Thank you, Maharaj. Yes, it is easy to agree that curiosity whets our passion. And he has tried to throw light on our ancient aviation system, on medicine, all are arguable points, but still we are open to everything. Next, I would like to call upon here Swami Dibbyanandaji Maharaj, Secretary Ramakrishna Mission, Sharadapet. He is a very, very brilliant one. Perhaps my students who do not know. he always serves the people who are suffering in prison.
Honorable guests, resource persons, and our sannyasins, dear students, participants, I am very happy to be here in this forenoon session, first session, inaugural session of this seminar or workshop. Yesterday I was in a valedictory session in the Department of Mining Engineering, IIT Kharagpur. There was, after some speeches, there was feedback from the participants. One junior but chief engineer of Vedanta in mining sector, he expressed his experience of the seminar, 4-day seminar. He told the subject was in mining, technology solution, selection of equipment in sustaining mining. He was telling, he opened his heart that I was not interested in mining, though I am now working in mining sector of Vedanta. But after coming to this seminar, I feel that mining is a very nice subject, and I feel interested now after this seminar. I also believe that after attending this seminar, science will be popularized to you, and you will also convey the message of science and the science, growth of science to the next generation. You will be very good teachers also in future. I know when we were taught in a July school at Purulia, my physics teacher, he did not confine himself in theories only. In the theoretical class itself, he used to bring many equipments of small instruments, demonstration work he used to do. In every field, he used to demonstrate, popularize, and our interest grew more and more in his class. Science is really a very interesting subject. I have a friend or a student, Dr. Tinku Acharya. He is in IT field. He has now more than 200 patents in different areas of IT. He's a very brilliant boy, but he lived in a cottage of only 40 square feet in a slum at Salkia, Howrah. He was selected for physics honors. He stood first in our college, but he did not join because at the age of 10, his father was paralyzed and he had to bear the load of 6 persons in the family. He used to work as a child labor and he continued. But he dreamed of being a very good computer scientist. He has achieved his goal, but still he works. And he is submitting paper, he is submitting patentship, and he will definitely have 400 or 500 patents in science. He has made a cottage in Howrah district in between Urubedia and Bagnan, and he meets students of rural area in different schools on Saturdays, and he requests them to study physics or science. Science is such a subject, it actually makes our brain transparent. We are being cheated. I know, you know, it has been told that I work in jails, which are now called correctional home. I have seen many people are totally innocent. They have been cheated by the society by the rich people, by the rulers, and they are now suffering in the jail, languishing in the jail, behind the bar for many years. Yesterday, I received a telephone call from Gangaram Das of Birbhum, who was in jail for 6 years, and he was acquitted for no fault of his own. If he would have been a science student, Tinku says that he would have been released earlier. Science students will never bend their spine. I am not criticizing other subjects or literature. My principal is from Bengali department. He is very good. He had scientific mind. And actually, our mind should be scientific. Sri Ramakrishna used to say, knowing about milk is knowledge, but taking milk and being strong is science. সায়েন্স বিজ্ঞান আমাদের জানতে হবে, জেনে শক্তি লাভ করতে হবে। বিজ্ঞান সত্যি আমাদের শক্তি দেবে। ইতিহাস থেকেও আমরা শক্তি পেতে পারি, ভূগোল থেকে শক্তি পেতে পারি, কিন্তু সায়েন্সে আমাদের সায়েন্স প্রয়োজন। কারণ ইন এভরিডে লাইফ, ইন ডেইলি লাইফ, উই ক্যানট লিভ উইদাউট সায়েন্স। উই ইউজ সায়েন্স। সো at least 50% of the people must study science, and we should not hanker after money. We should not go for only IAS or BCS or IPS. Our students should strive for becoming academician, research scholars, guides, professors, and leading scientists. You are to be. We have here two persons who were in the afternoon, one will come, and now in front of us our Vikramjit Bose is sitting. He is a great scientist. So, Bhatnagar awardee, you are to dream for that. Those who have come here, please try to study science sincerely and live scientific life, so that you also will be a very popular scientist. Yes, science is to be popularized. You dive deep in mathematics, in physics, in chemistry, in material science, then you will go, if you go to the deep, then you will have jewels, pearls, and many rich things which cannot be had with money only. If you learn more and more, if you know the depth of science, then more than money you will achieve. Really, this should be thought. But remember that science has no moral dimension. It is also like a knife. You give it to a murderer and a surgeon. Both will use it differently. So science is to be used for the welfare of people. You should not cheat people because you are a very great scholar. At least you should not harm anybody. You should know it, and you should develop science, scientific mind to enrich the world. You know, recently I was reading a book, SQ, Spirituality Quotient, by Dana Johar and another co-author. Dana Johar is a PhD from MIT, America, and she was one day taking her 5-year-old child to bed at night. Then the baby, the child of 5 years, asked her a very good question, but it was unknown to her. He asked, "Mom, why God has given me birth in this world? And why the God is keeping me alive? Can you tell me?" A student of physics, she could not answer on that day. So she asked for a fortnight time. মা আমাকে কেন ভগবান জন্ম দিয়েছেন 5 বছরের শিশু জিজ্ঞেস করছে, আর কেনই বা আমাকে বাঁচিয়ে রেখেছেন? আমরা কি এই প্রশ্ন করি কখনো? এখনো করি না, বয়স হলেও করি না। 80 বছরের মানুষও এই প্রশ্ন করতে ভুলে যায়, প্রশ্ন আসে না মনে। সত্যি এটা একটা জিজ্ঞাসা, এও একটা বিজ্ঞান। এই বিজ্ঞান যখন করলো মা বিজ্ঞানী পদার্থবিদ, মা নার্ভাস হয়ে গিয়েছিলেন। নার্ভাস ঠিক হননি, বললেন 14 দিন সময় দাও, আমি একটু ভেবে দেখি। মা অনেক ডুব দিলেন। ঠাকুরের গান আছে, ডুব 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 রূপসাগরে আমার মন, তলাতল পাতাল খুঁজলে পাবি রে প্রেম রত্নধন। 14 দিন 15 দিন পরে উনি বললেন, টু মেক দি ওয়ার্ল্ড বেটার, টু লিড দি ওয়ার্ল্ড টু এ বেটার প্লেস, ফর দ্যাট গড হ্যাজ গিভেন ইউ বার্থ। ভগবান জন্ম দিয়েছেন তোমাকে এই কারণে, পৃথিবীটাকে সুন্দরতর করার জন্য, আর সেই জন্যই বাঁচিয়ে রেখেছেন। সত্যি সায়েন্টিস্টদের স্বপ্ন এটাই। কোন সায়েন্টিস্ট ওই মারণাস্ত্র আবিষ্কার করেননি, মারবার জন্য মারণাস্ত্র আবিষ্কার হয়নি। নিউক্লিয়ার পাওয়ার যখন তৈরি হয়েছিল, এটা মানব কল্যাণের জন্যই তৈরি হয়েছে, জানতে হবে। আমরা কোনোদিন কোনো বিজ্ঞানী চান না, আমি দেখেছি ড্রাইভাররা গাড়ি চালান যখন সামনে যদি একটা সাপ পড়ে না, কিংবা একটা ছোট্ট কীট পতঙ্গ থাকে, তাকেও আঘাত করতে চায় না। বিজ্ঞানীরা কোনোদিন মার্ডারার হতে পারেন না সোসাইটির কোনো সময়। এই আমরা জাপানে একটা গ্যাস লিকের সময় শুনেছিলাম, কাগজে দেখেছি, আমি তো বিশ্বাস করি না তারা বিজ্ঞানী কিনা, যে গ্যাস লিকের সময় কিছু বিজ্ঞানীরাও অ্যাসোসিয়েট ছিলেন। কিন্তু এটা বিজ্ঞানের ধর্ম নয়। বিজ্ঞান সব সময় মানব কল্যাণে ব্রতী থাকে বা ব্রতী থাকবে। তোমরা এইরকম বিজ্ঞানী হবে। এবং আমি আর সময় নেব না, তোমাদের অনুরোধ করব, বিজ্ঞান সাধনা তোমরা ব্রতী হবে আগামী দিনে, এবং কেউ ডাইভার্ট করবে না। যারা সায়েন্সে আছো, এই 12-এ পড়ছো বা 11-এ পড়ছো, এখন তোমরা সায়েন্সেই থেকো দয়া করে। ম্যানেজমেন্টে গিয়ে ওই অর্থের জন্য কোনো বড় কোম্পানির ম্যানেজার হতে যেও না। দয়া করে বিজ্ঞান পড়ো, বিজ্ঞানে ডুব দাও এবং বৈজ্ঞানিকের মতো চিন্তা করো। আমি মাঝে মাঝে জানো ছেলে মেয়েদের ছোট্ট একটা প্রশ্ন করি, 58-কে 18 দিয়ে গুণ করলে কি হবে? মাল্টিপ্লাই 18 into 58 উইদাউট মাল্টিপ্লাইং 18 and 58। ছেলে মেয়েরা বলতে পারে না, বলে ক্যালকুলেটর নেই, কাগজ কলম নেই, কি করে করব। আমি বললাম, জানো একটি চাল বিক্রেতা মহিলা, তিনি এক মাস্টারমশাইকে চাল দিয়েছিলেন। এক বোরা চাল দেখে মাস্টারমশাই বললেন কত হবে, ওর অ্যাপ্রক্সিমেশন ছিল জানা, বললেন বাবু 60 কিলোর মতো হবে, দেখি। তারপরে উনি ওজন করে দিলেন 58 কিলোগ্রাম at the rate of 18। মাস্টারমশাই জিজ্ঞেস করলেন, হোয়াট শুড বি দি কস্ট, হাউ মাচ আই এম টু পে? সি টোল্ড, ইউ গিভ মি 1044। তারপরে উনি জিজ্ঞেস করলেন কোন ক্লাস অব্দি পড়েছেন? তখন উনি বললেন, আমি কখনো স্কুলের চৌকাঠ পেরোইনি। কি করে এই গুণটা করলেন? উনি বলেন, আমার মেয়েটা ক্লাস 4-এ পড়ে, তার কাছে আমি 18-এ মাল্টিপ্লিকেশন শিখে নিয়েছি। I multiplied 18 and 6 mentally, 108. I put a 0 on the right side. 1080 is the cost of 60 kilogram. I subtracted 18 into 2, 36 from that, and I got 1044. এইভাবে কিন্তু ওই ওরা ক্যালকুলেশন করে। তোমরাও হাঁটতে ফিরতে বড় বড় ফর্মুলা, অঙ্ক, এই সায়েন্স ফিজিক্সের, সেইগুলো যদি তোমরা ওই ব্রুডিং করার মতো করতে পারো। আমার মাস্টারমশাই বলতেন, তিনি সায়েন্সের ছিলেন না আর্টসের ছিলেন আমার মনে নেই, মাস্টার দাশগুপ্ত বলে, তিনি বলেছিলেন, বিজ্ঞানের ছেলেরা তোমরা ম্যাথামেটিক্সের সব ফর্মুলাগুলো একটা বড় আর্ট পেপারে লিখে রাখো। ফিজিক্সের এরকম ডেফিনেশন ফর্মুলাগুলো আর্ট পেপারে বেসিক জিনিসগুলো লিখে রাখো, ফাউন্ডেশন যেগুলো। তারপরে কেমিস্ট্রিরও এরকম যেগুলো খুব নেসেসারি, সব সময় চলতে ফিরতে লাগে, সেগুলো আর্ট পেপারে লিখে তোমার ঘরে স্টাডি রুমে দেওয়ালে পেস্ট করে দাও। আর ওই ভাইব্রেশনের মধ্যে থাকবে, ওইগুলো মনে করতে থাকবে সব সময়। অন্য হালকা চিন্তায় সময় দেবে না, ডুব দাও। এইটুকু অনুরোধ করে আমি আজকের এই সেমিনার সফল হোক। তোমরা যোগাযোগ রাখবে মাস্টারমশাইদের সাথে, পরবর্তীকালে যখন কাজ করবে, যেখানেই অসুবিধা হবে, ভালো ভালো শিক্ষক আছেন, এখনো সিনিয়ররা আছেন অনেক। তোমাদেরও চলে যাওয়ার পরে স্কুল ছেড়ে আমাদের নরেন্দ্রপুরে যারা পড়ে, নরেন্দ্রপুরের টিচাররা কন্ট্যাক্ট রাখেন। তোমরাও তোমাদের শিক্ষকদের সাথে, শিক্ষিকাদের সাথে কন্ট্যাক্ট রাখবে। পড়া চলার পথে যেখানে বিজ্ঞান সাধনায় অসুবিধে হবে, তাদের সাহায্য নেবে এবং এগিয়ে যাবে সামনের দিকে। লক্ষ্য কিন্তু মহারাজ বলে গেছেন আগে, অনেক দূর, শেষ নেই যাত্রার কোনোদিন। তাই বিজ্ঞানীরা থামেন না। আমাদের বেদেও আছে কথা, চড়াই বেতি, চড়াই বেতি। আর যে চলে, দেবতারা তার হাত ধরে এগিয়ে নিয়ে যান। যারা এখানে গবেষণা করেছেন, পড়েছেন, তারা জানেন কত অডসের মধ্যে দিয়ে তাদেরও সাধনা করতে হয়েছে। যে কোনো মানুষ কোনোদিনই ওই ফ্লাওয়ার বেডের উপরে শুয়ে থাকতে পারে না। যারা চলে, যারা বড় হয়, তাদের অনেক কষ্ট করে সংগ্রাম করতে হয়। দেখবে টমাস আলভা এডিসন, তিনি বোধহয় 10,000 বার ফেলিওর হয়েছিলেন, তারপরে বাল্ব, ইলেকট্রিক বাল্বের আবিষ্কার করেছিলেন। ওর কারখানাটা পুড়ে গিয়েছিল, অনেক সম্পত্তি নষ্ট হয়ে গেল, কিন্তু বলেন আমি আবার ফ্রেশ তৈরি করব। এটা আমার কাছে একটা শিক্ষা যে সবকিছু টেম্পোরারি। অদ্ভুত ভাবে বিজ্ঞানীরা কিন্তু এগিয়ে গেছেন, এখনো এরকমের অনেক আমরা ঘটনা পাই। এইটুকু বলে সকলকে আবার আমি শুভেচ্ছা জানাই, যারা উদ্যোক্তা, যারা এসেছেন, পার্টিসিপেন্ট, সকলকে নমস্কার।
Thank you, Maharaj, for your motivational lecture. Now I would like to request Shastrogyananda, better known as Sanjeev Maharaj, the principal of Belur Vidyamandira. Please.
Om Namo Bhagavate Sri Ramakrishna. My devoted pranams to the holy feet of revered Srimad Swami Vidyamandira Ji Maharaj, revered Srimad Swami Sarvalokananda Ji Maharaj, and all the revered Swamis who are in the auditorium. My respectful namaskar and warm regards to great scientists like Professor Malik, Professor Manna, Professor Basu, Professor Dasgupta, and we will be coming later. And my hearty congratulations and namaskar to our Shandipan Maharaj, Turiya Chaitanya, and other Brahmachari Maharajas and other Swamis too, and also the students who have assembled here today to listen to the motivational talks of our renowned scientist of the day. In fact, I was not prepared to speak to you, but revered Sarvalokananda Ji Maharaj and Vidyamandira Maharaj were told that you should speak some words to them. It's true that I belong to the discipline of literature and language, but what Maharaj has told is it's right, very much right, that it's not the scientific experimentation, neither the scientific observation, rather is the scientific temperament, the scientific mind, which makes the scientific invention possible. If you have read the history of human civilization, if you have gone through the length and breadth of the scientific history of our humanity, you will be surprised to note that even the people who did not belong academically to the science or technology discovered many important things for the posterior, for the development of the human civilization. So here, today, these young students, the fresh minds who have come here to listen to the talks of our great scientists of the country, I think you will remember that on you are the responsibility to lead the scientific world, the scientific community, the scientific mind. Whenever we study, whenever we try to go in the depth of the knowledge domain, we must remember that there is no space, there is no room to feel myself complacent, to feel myself satisfied. The satisfaction in science or in any discipline of knowledge will never open up new horizons. So the discontent, as it is called in the spiritual science, divine discontent, is always very much required in our study, in our knowledge, in the progression of our knowledge. So dear students, when you have come here today and when you are preparing yourself to listen to the great minds of India today, I think you will try to learn from them this, how they are keeping this, they are sustaining this divine discontent in their mind when they are going for their scientific research. Innovation, reasoning, and this divine discontent are the three pillars in any type of knowledge, in any type of scientific discovery. So remember that only coming here and sitting within an auditorium and listening and just spending hours listening to the talks in comfort is not our aim today. Rather, we would request you, we would pray to Almighty that they would give you this energetic mind to receive this inspiration from the scientific leaders of this country who have come to you. So this, if you receive the inspiration, if you are inspired at the end of the session, then only we will be happy to note that yes, our endeavor is successful. I think all of you have seen in the athletics meet the famous relay race. In the relay race, what happens, the former runner just hands over the baton to the successor runner. So what does he want to communicate to the successor runner? Once I asked one runner in the athletics meet, the student told me, I told him that my successor one, I told him, go faster and do better. So we will be able to achieve the feat. Today you have seen Professor Mollik, Professor Manna, Professor Dasgupta and many other seniors have come here only to hand over their baton to you. They are the predecessor runner. You are the successor runners. They will hand over the baton of scientific temperament to you. They will hand over their baton of the scientific inspiration to you, the scientific the scientific discontent to you, so that you will lead the fresh run for the posterity. If you can do that, remember, they will be more pleased, they will be happy, and they will think, yes, their achievements have really seen the success. And that is the motto of this conference, this workshop today. Thank you.
Thank you very much, Maharaj. So we are running on time. Now I would like to request Professor Bikramjit Basu.
So good morning everybody, it's a great pleasure to be here. I mean, we all consider Narendra Ramakrishna Mission as a temple of education because, when I was a child and a schoolboy, it was a dream to study at Ramakrishna Mission school, which I could not do. But in any case, it's a great pleasure to be here, and today's national workshop is being financially sponsored by American Ceramic Society through Ceramic Class and Innovation Foundation. We are extremely pleased to have Professor Ashok Kumar Mollik with us. He is a teacher par excellence. When I started my career at IIT Kanpur, we used to look up at him as one of the role models. And Professor Ashok Mollik is also a distinguished teacher of IIT Kanpur. He has many awards and accolades to his credit, which I'm not going to mention in details, but certainly I'm sure you all will enjoy his lecture. He is actively popularizing science among school students. And after Professor Mollik, we'll have another distinguished speaker, Professor Indranil Manna, who is considered to be most influential engineer in our time, current in Indian scenario, national scenario. He is leading many of the national scheme like Imprint, and he was former director of IIT Kanpur. Again, he is one of the role models for many of us in India. And subsequently, we have Professor Tanushree Dasgupta from Indian Association of Cultivation Science, and one of the distinguished physicists, and Rahul also will be joining us. I'm sure that you all will enjoy all the lectures, and my sincere request would be that I mean, our efforts would be our efforts would be fruitful if you all take up science as career. Thank you very much.
Let me start by thanking the organizers for giving me this opportunity to be a participant in this particular event with so many young students in front of me. You might be wondering that the seminar has been titled Recent Advances, and you are finding the most ancient person on the stage, right? And that is the only qualification I had to sit along with the dignitaries here. Let me start that it is recent advances in science and technology, but you are starting with mathematics. Is mathematics a science? If you know, the first modern scientist was Galileo, and he said, objective of science is to unlock the secrets of nature, and the language of secret of nature is written by the language of geometry. That means science can be expressed only through the language of mathematics. So mathematics that way may not be a part of science, but you cannot do science without mathematics. Okay? Now, as you see, I am not a mathematician, I am not even a teacher of mathematics, right? So you don't expect much of mathematics in this talk, you will find a little bit of magic. And because the magic is due to the magician known as Ramanujan. Okay. In the modern era, Srinivasa Ramanujan is undoubtedly the most famous and the most brilliant mathematician that India has produced. He was born in, as you see, 22nd December 1887 and died very early, 26th April 1920. That means he lived less than 33 years. Not only he had such a short lifespan, he also faced certain other difficulties. One is, his financial condition was very bad for most of his life. His health was having a lot of problems during his pre-productive period. And third, he didn't have any training, formal training in higher mathematics. But the third point, people have debate whether it is a disadvantage or advantage. Because he didn't have formal training, he had the courage of creating mathematics. He was not biased by the previous mathematics. So he rediscovered a lot of things and also had the boldness and courage to do totally new mathematics. In fact, so far innate mathematical ability is concerned, his contemporaries told that he is just next to Gauss and Euler. This is the best biography of Ramanujan written by Professor Robert Kanigal, which has been translated into various languages including Bengali. In fact, one of your revered teacher of Narendrapur Ramakrishna Mission, Partho Babu, has translated it to Bengali, Antohiner Antorjami. It's a very good translation. If you have not read it, please read it. You know, Ramanujan was so poor that he did most of his mathematics on slate because he couldn't afford papers. So only the final result he used to write in his notebook. So his thought process has been lost forever. One of his notebook was rediscovered in Cambridge Archive in 1976. That is more than 50 years after his death. And it contains 600 new results and theorems which are keeping mathematicians busy even till today. He had the fantastic ability that you tell him any number, immediately he will tell you what is the special characteristics of that number. So much so that Professor Littlewood, the famous British mathematician of that time, said that all natural numbers were his personal friends. That's why he knows so much about them. So I will discuss only these magical aspects of Ramanujan mathematics without proof and other things. And the best place to start magic is probably magic square. Do you know this is a magic square? It is a 3 by 3 magic square. You see 1 to 9 is written in such a way that if you add up, can you hear me? If you add up any row, any column or the principal diagonal, you get the same number 15. Right? It is a 3 by 3 magic square. Do you know how to make such magic squares? How many of you know it? Please raise your hand. Okay, then I think I should teach you. It is very simple. You can make odd order magic square of any order. It is a 3 by 3, you can make 5 by 5, 7 by 7 if you follow only two rules very mechanically. You write 1 in the middle top. In the middle box of the top row, you write 1. Then you always try to go diagonally to the right. So if you go there, you see you are going outside the square by cutting across this boundary line. In that case, you come down at the bottom of this row. 2. So you write 3 here, you are cutting across this boundary line, so go to the other extreme, write 3. This is one rule. Whenever you are cutting across a boundary line, go to the extreme box. Now 3, you want to write here, but it's already filled up. So here comes the second rule. If it is already filled up, you just come down. You write 4. 4, 5, 6. Again you are going out, but now you are going out through a corner, not through a line. Right? And if you go out to the corner, then just come one step below, just like here. 3 to 4, 6 to 7. Again you are crossing the boundary line, so go to the other extreme, 8. Again you are crossing the boundary line, go to the other extreme, 9. That's all. You don't need anything else. Have you understood it? Okay. If you have understood it, then you should be able to make this 5 by 5, 7 by 7, 9 by 9, anything. 5 by 9, let me go through quickly that I didn't cheat you. 1, going out, 2, 3, going out, 4, 5, filled up, 6, 7, 8, going out, 9, going out, 10, filled up, come down, 11, 12, 13, 14, 15, going out through the corner, so come down, 16, going out, go to the other extreme, 17, going out, go to the other extreme, 18, 19, 20, is filled up, so come down, 21, 22, going out, 23, 24, you are going out, 25. If you add up, you will get 65, whether any row, any column, or any principal diagonal. Okay, it's the magic. So let me start with this magic of mathematics. It is so easy for any order, but as soon as you go to even order, if you want to make a 4 by 4 magic square, then there is no such universal rule that I can make any even order magic square. The most famous magic square of even order was done by this German painter. That's what shows that you need not be a mathematician. You can play with mathematics. Even you see, he is Albert Dürer, he was a painter. This is a very famous painting of his mother, Melancholia, that was drawn in 1514. This painting is so famous because 16th century German village, all the details are available here. And if you can notice here, there is a 4 by 4 magic square. Actually, Dürer was so pleased with his own discovery of 4 by 4 magic square, he knew that as a mathematician, you will remember him. So he included in his painting, because he knew his painting will last 400 years, even we know it today. So he made it immortal. And what is this magic square you see? Why it is so famous? Here is written 1 to 16. But I cannot tell you any rule. This is a little variation of an Indian magic square of about 4,000 years ago. And here, if you add any row, any column or principal diagonal, it is 34. No problem. But it has other properties. Even if you add only the corner values, you see it is again 34. 16 plus 4, 20, 13 plus 1, 14, 34. If you add this 4, this 4, this 4 or this 4, again is 34. So it is more than super magic square, right? Even if you add 8, 3, 9 and 14, you will get 34. If you get 12, 2, 5, 15, you will get 34. If you add 3, 2, 14 and 15, 34, 5, 9, 12 and 8, 34. So you are just unable to get out of 34 by almost taking any combination. So he was very pleased with this. Here also again, 12, 3, 5, 14, 34. This is Albert Dürer, I would say super magic square of 4 by 4. Okay. Now let us come to Ramanujan magic square. Albert Dürer wrote 1 to 16, right? But if you remember Ramanujan's birthday, okay, let me tell you that In internet it is said Ramanujan's magic square, but I have not been able to locate where Ramanujan did it. So I would prefer to call it in honor of Ramanujan. Maybe somebody else has made it and put it in the internet. Internet, so you don't have any responsibility. You can put up anything. So in honor of Ramanujan, this register said, if you remember the date of birth of Ramanujan, 22nd December 1887. So what is done? You write 22 December 1887. Not 1 to 16. You fill up the first row with his date of birth. And fill up the other 12 numbers in such a way that it becomes Albert Durer magic square. Not only it has rows and columns and principal diagonals, but all other combinations like 4 corners. If you add up, you will get 139. If you add up the same color, you will get 139. Again, what I showed earlier for Albert Durer magic square, this red square, if you add up, it will get 139. You are unable to go out of 139. If you add up these 4 central, this thing, 139. Even these 4 blocks, everything adds up to the same number, 139. And it is a little more than Albert Durer magic square. Up to this point, it is same as Albert Durer magic square. Albert Durer magic square satisfied all these conditions. But here, these 4 and these 4 are again 139. But you see Albert Durer magic square, this 4 is add to 15, 21, 30. And this is 38. Not 34 and 34. But here, these 4 and these 4 also add up to 139. So I think enough of the same magic square, right? Let us see what Ramanujan did. There is famous thing which is known as taxi cab number. Most of you have heard this, right? And maybe you've seen it in the Ramanujan movie. Right. This is the cartoon that his mentor in England, Godfrey Harold Hardy, Ramanujan was ill. He was hospitalized and he was in a hospital in London, Putnam area. So Hardy one day came to visit him. And just to start the conversation, he found Ramanujan a little depressed. So he said, Ramanujan, I came by a taxi number which is very boring. It's 1729. I think such a bad number doesn't have any bad omen. Ramanujan immediately jumped and said, no, Hardy, this is a very interesting number, you know. This is the smallest number that can be represented as sum of 2 squares cubes in 2 different ways. 10 cube plus 9 cube is 1729. 12 cubes plus 1 cube is 1729. There is no number below this which has this property. So then onwards it became famous as taxi cab number. But so Hardy was very surprised that how could he say it so quickly? What was not known, that has been found only after Ramanujan's lost notebook was rediscovered. That Ramanujan played with this number in various ways throughout his life. That's why 1729 was such a famous number to him. All of you know, heard of this, right? X to the power n plus y to the power n equal to z to the power n. With x, y, z integers is not possible for any n greater than 2. 3 square plus 4 square is 5 square, right? Pythagorean. But you cannot find some a cube plus b cube equal to c cube. And this was proved by Euler that you cannot do it for n equal to 3. Fermat's conjecture is for any n greater than 2 it is not possible, which has been proved only in 1994 after 350 years. But this Euler proved that it is not possible with n equal to 3. So what Ramanujan searched for, okay, it cannot be equal to, but can I have x cube plus y cube a little different from z cube, either plus 1 or minus 1? Are there any such x, y, z integers which satisfy this? Little defective. Equal to it not possible. So let it be just 1 more or 1 less. And there he found 10 cube plus 9 cube is 12 cube plus 1. To Hardy he said 1 cubed. 1 and 1 cube does same. And 6 cube plus 8 cube is 9 cube minus 1. So he found this. Yes, such numbers exist. But Ramanujan being a mathematician, not a child, what he said, what are the other combinations? What are the other combinations satisfying this? how to get more such numbers. And his identity is from his lost notebook. This is a page from his notebook. His handwriting is very neat in this notebook. He said, if this is equal to this polynomial, this equal to this polynomial, because coefficients are a0, a1, a2 and all that, then an cube plus bn cube will be cn cube plus minus minus 1 to the power n. If n is odd, it will be minus 1. If n is even, then it will be plus 1. So he wrote this. 9 cube plus 10 cube is 12 cube plus 1. 6 cube plus 8 cube is 9 cube minus 1. This is first. Second one he wrote this. Third one he wrote this. But there is no other indication how he got these numbers and how to generate more such numbers. But he knew that this is true. 9 cube plus 10 cube is 12 cube plus 1. This is the same thing I have written. So an cube plus bn cube plus cn cube minus 1 to the power n. He wrote 4 sets of a and bn, but beyond that, nobody knew how he got those. So it was obviously before 1920. In 2004, one fellow could come up with the result that you can get a and b and c n from this matrix to the power n multiplied by this column matrix. Maybe class 12 or college students have heard of matrix. Okay? So this is done in 2004. More than 80 years after Ramanujan's death. And if you put n equal to 1 and n equal to 2, you get these numbers which Ramanujan wrote in his diary, lost notebook. Not only that, these are results, as I said, Ramanujan wrote one set more, but if you put n equal to 2, you get this, n equal to 3, you will get the next set, n 3 and 4. Not only that, he arrived at this number in a different way also. Ramanujan's notebook contains this following formula. If u and v are arbitrary integers, positive or negative, and we define a, b, c, d in terms of u and v. U and v are any integers, positive or negative, and then if I define a, b, c, d, you see the coefficients. What are the coefficients? 3, 4, 5 and 6. So you know 3 square plus 4 square is 5 square. But did you notice that 3 cube plus 4 cube plus 5 cube is 6 cubed? Just see. 3 square plus 4 square equal to 5 square, all of you know. But 3 cube plus 4 cube plus 5 cube is equal to 6 cubed. It is 3, 4, 5 is the Pythagorean rectangular right angle triangle, right? 3, 4, 5 sides is the right angle triangle. 5 is the hypotenuse, 3 and 4 are the other two sides. Area of that triangle is 6. 4 consecutive integers, 3, 4, 5, 6. So Ramanujan obviously knew it, and then he said, if this is true, then a cube plus b cube plus c cube will be d cubed. That you can check. It is a little more algebra, few pages, but you can get it. And then if you put u equal to 1 and v equal to minus 2, you will get from this a, b, c, d like this. Minus 27, 36, 3 and 30. So a cube plus b cube plus c cube equal to d cube will give you this. Now if you take 9 cube common, you get, this is 3 cube. 3 cube common, sorry. Not 3 cube if you take common, this is 1 cube plus 12 cube, 9 cube plus 10 cube. It is the same result. Taxi cab number. So Ramanujan, it was appeared as magic to everybody else, but for Ramanujan it is real mathematics. There is no magic in it. It is the two Indian mathematicians in that time. Pillai was also in Cambridge. He is quite famous. So this Professor Chawla wrote to Pillai that this probably is the smallest integer that can be expressed as sum of two positive cubes in 3 different ways. Not 2 different ways, like taxi cab number. 3 different ways. So those days there was no computer, so nobody could check it. But now we know that it is actually the 4th such number. Smallest one is this. You see, this is this cube plus this cube, this cube plus this cube, this cube plus this cube. So you can write this number in 3 different ways, the sum of 2 cubes. So this is called taxicab number of order 3. 1729 was the taxicab number of order 2. And mathematicians are very close to what you call insane, so they keep on doing such things. And now with supercomputer, they have gone up to T6, T4, T5, T6, and they have proved that there are taxicab numbers of all orders. How to find them is a different question, because T4 is this number, this cube plus this cube, this cube plus this cube, this cube plus this cube, this cube plus this. This is a T4 number, and this is a T5 number, and this is a T6 number. And this can be done only with supercomputers. Even a normal computer, you can't do these calculations. But, well, I'm sure when you come here and give the lecture, maybe you will say, this is T7 and T8. That's how things progress. Who will stop me? You stop me. Okay. Pi is a very famous mathematical constant, all of you know, the first universal constant in mathematics. And some of you, the senior students at least, may know this series, that how to calculate pi. Pi you cannot never finish writing. Whether it is a number or not is a question. You can never write what is pi. Pi you can only write pi, because there is no end to it. So this is an infinite series which is very famous because it approximates pi by 4. It was done by Leibniz and Gregory, and even Newton appreciated this, Leibniz, which is very rare event. Newton and Leibniz didn't like each other. Actually, this was done by Indian mathematician Madhava in 14th century, and this is the 17th century. That means 300 years ago, the same series was given by Madhava. But those days it was on Sriti and Shruti, there was nothing in writing. It is only few generations later mathematicians wrote it, that Nilakantha, he wrote that Madhava did it. But this is an useless series, because if you take 500 terms, then the value of pi is calculated correct up to 3 decimal place. And all of you can rattle out 3.14125, right? 34159, the value of pi. It gives 500 terms it takes to give 3 decimal place accuracy. Ramanujan, because as you know, he didn't know, he rediscovered this Bauer series, which is very efficient. But what he did in 1910 is mind-boggling. He wrote this series for pi. And you know what is the beauty of this series? If you take only one term, k equal to 0, you get the value of pi correct to 8 decimal place. The previous series, Gregory series, you remember 500 terms for 3 decimal place accuracy. Here 1 term for 8 decimal place accuracy, and every term you add, you get 8 more decimal place of accuracy. So this was a fantastic discovery of Ramanujan. Actually, a little variation of this done by 2 Russian brothers is still the fastest algorithm for computing pi, and pi has been computed up to trillion decimal places. Oh, well, mathematicians do it, and there are purpose of that. Maybe this is not the place to discuss it, but pi has been calculated up to trillion decimal place. And this is the Russian, it's in 1994. You see, very similar to Ramanujan series, right? It looks very similar. The factorial was there, instead of 6k there was 4k, something k factorial, and then something to the power k. So this gives 14 decimal place of accuracy the first term, and every additional term gives 14 more. Okay, I'll just give one more. Another famous approximation of Ramanujan. You know pi equal to 3 into 1 by 7, right? 3 plus 1 by 7. 3 1 by 7 you write for pi, and he writes for pi to the power 4, 97 9 by 22. How accurate it is? You see, 97 plus this continued fraction if you neglect this 1 upon 16,000 in comparison to 1, there is very little error. And if you neglect that, you get this. And Ramanujan, as I said, is all looked like magic, because this number is now known as Ramanujan's constant, because E, all of you have heard this number E. That is again a right number you cannot write. It is an infinite series, transcendental number. To the power square root of 163, which is an irrational number. Pi is again a transcendental number. So Ramanujan claimed that this number is very close to an integer. It looked monstrous. Must be a transcendental number. I can believe it. That you can never finish writing this number. But Ramanujan said this is very close to an integer. That's why it is called Ramanujan's constant. Because now with computer, what people have found, this number is this. Can you see 18 numbers? Then decimal. Then the decimal point is followed by 12 nines. It is almost an integer, right? And 163 is a very special number. It is the last of the Huygens number. Well, that if you do number theory, then you will come to know what is Huygens number. It's complex number. This is a very pivotal role to play. In 1911, Ramanujan posed this following problem to the readers of Indian Mathematical Journal. That what is this left hand side? He writes the right hand side. And for 3 months nobody could answer it. Then Ramanujan gave the answer is 3. And this continues infinite nested radicals. So why it is 3? Okay, if the answer is given, then I can also do it. Because if you give me 3 as the left hand side, I can get the right hand side. Very simply. You write 3 is square root of 9 is 1 plus 8. 8 is 2 into 4. 4 is square root of 16. So you get 2. 16 is 1 plus 15. 3 into 5. So you get 3 into 25. So you see, you are generating the right hand side. But Ramanujan's magic is that she gave the right hand side and asked you to find the left hand side. Okay, I'll stop. Should I stop or I should continue for a few more minutes? It's your choice. Okay, so this is what it is. But don't think mathematics is so simple. I can write even 4 like this. Then the answer is 3 or 4. Because if I want, I can write 4 like this. 4 is square root of 16, which is 1 plus 15. 15 is 2 into 15 by 2, which is 2 into square root of 225 by 4. So this is 1 plus 221 by 4. I can get the right hand side, but now I have 4. So which one is correct? 3 or 4? It is obviously 3. Because 3 you can generalize very easily. You write this is n and this is n plus 2 whole square, right? 4 square, n plus 2 whole square. Then you can do a little algebra and you can see n is generating n plus 1, n plus 2 has been replaced by n plus 3. So in the next step, n plus 1 will be replaced by n plus 2, n plus 3 will be replaced by n plus 4, and you can generate the entire series starting from n equal to 2. But Ramanujan didn't do it this way. He said, this is a general result. Now you put x equal to 2. This is true for all values of x. And if you put x equal to 2, you get that 3 equal to that. Now the question is why this is true. Ramanujan wrote it. What Ramanujan did, he said this is true because this is true. It all really appears like absolute magic to even the highest level of mathematicians. Forget about us. Because this is true for all values of x, n and a. So what he does, I obviously don't know why, but I can verify it. Verify it you can easily. Square both sides. Square both sides, so this thing comes out of the square root sign. And this is f of x plus n, because x has been replaced by x plus n every year. So this is this. So a square minus b square. You take it to the other side, you can write this. Now you see, if the first on the left hand side is equal to x, then this automatically becomes this. So this must be true. This is verification, this is not a proof. Okay, this I'll omit because this is something which this was a problem given in the same Indian Journal of the Indian Mathematical Society. Ramanujan gave the solution in 1912 that obtain this in closed form. He gave this. You see? M equal to 0 to infinity, that series is summed up to this. And it all appears as a magic because he didn't bother about something, he didn't know complex analysis. So whatever is true for real variable, he used that for complex variable and got the result. So that will not be accepted as mathematical proof, but people cannot deny it because this is what you get by adding term by term for 200 terms, and this is Ramanujan's result. I think both are identical. So he said that every mathematical equation expresses the wish of God. If it does not express the wish of God, then this equation is of no value. So he thought everything comes to his mind. Let's stop. Okay. Just something. I'll come to that last two slides, which is very important. Okay. Can I take a commercial break because audiovisual programs normally have. Yes, this is a commercial break because all that I was saying you can find in this book, and this book is written by me. I am advertising my own book, so I call it commercial break. Ramanujan's creativity and magical ways of producing new mathematical results are sometimes attributed to his lack of formal mathematics education. He himself attributed it to the grace of goddess Namagini. And some Western scientists thought this is absolute bhagwas. I mean, they don't believe in such things. But what they forgot, that even great Western mathematicians, including Gauss, Pascal, Cantor, Littlewood, also believed that inspiration had a divine aspect. Even Gauss, considered as the greatest mathematician, said once that he proved a theorem not by dint of painful effort, but to speak by the grace of God. And again, a commercial break I end with the second part of my lecture, which I didn't present because initially I thought I'll get 1 hour, then I said 45 minutes now. It is a little less than that. So this is the last commercial break, that if you find this story of numbers, then you will get most of the results that I wanted to present in the second half. Thank you.
I was really sorry because our hands are tired by the hands of clock.
Yes.
So we have to look at it. Understand? So if you have any doubt, please clear it. And quick questions, if you have any, to the audience. Otherwise, we'll move to the next program. May I request Professor Indranil Vanna, please come up on the stage. So I think you have no question. Have you any question? Will you raise your hand?
But most of your questions will be answered in those books.
One of them is raising it. Please come up. Please come up here. If you have a strong voice, you can throw there.
Can you shout like me? Yeah.
So for that,
Yes.
for that formula that a cube plus b cube plus c cube equal to d cube, you gave that u square that huge formula with 3, 5, 4 and 6. Will it work for b equal to u?
No, you are getting b in terms of u. You see, you cannot, only thing you can arbitrarily assume is u and v, not ABCD.
No, can we assume u and v equal to each other?
Yes, sure.
Okay, thank
U
you.
equal to V, I heard V. 73-year-old years, don't get the high frequencies.
One is scratching his head. Are you ready to ask any question? Okay, please. We are now going to felicitate Professor Malik and Professor Inanil Manna could you please give us the applause.
So good afternoon, and so Professor Malik has already initiated you to mathematics, the language of science. So I hope by now things are going to be a lot more easier. So at the very beginning, I would like to express my gratitude to the organizers to give me my first ever, to make my first ever visit to Ramakrishna Mission Narendra possible. I always have admired this institution, which becomes a temple, no less than a temple. I always admired it from a distance because many of my friends during my college days and subsequent years had the privilege of studying in this great institution. So this has always been a dream for me that someday I'll come and visit. In fact, today while sitting here, I text to some of my friends who actually graduated from this place many years ago, and they all are very happy that today I'm here to share some of my thoughts with you. Let me also make it sort of a clarifier at the very beginning that all that I'm not now going to talk about is entirely my own views and not necessarily any established definition. And at the end, if you have queries, or even in the middle, I'll be very happy to answer. So the organizers gave me an advice that choose a topic which will be fairly easy to follow for the school children. And I am very passionate about a certain theme, and I chose a topic which you'll find very easy to follow. And my only job is to reveal before you that the principal theme is very simple, that the notion that I've written at the very top, science, engineering and technology, many of us make a very dangerous mistake of treating them as disparate, compartmentalized domains. But actually they are highly interrelated. In fact, they are not only interrelated, they are bound in a closed loop. And that's exactly the thesis that I'm going to present for you. Much of it will be derived from some of the examples at least will be derived from the days when I was associated with a CSL laboratory, not too far from here. Many of you would have seen Central Glass and Ceramic Research Institute. And I'll end with a national initiative to which Vikram alluded at the beginning, called Imprint, and why these are important today. That's exactly what I would like to explain. So this is how I would like to define the domains of science, engineering, and technology. And might sound very trivial, but actually you realize that this is really profound. Say about more than 300, maybe close to 400 years ago, when an apple, nobody knows whether it really fell on Newton's head or not, but the apple always would fall to the ground, and it was the genius of Newton, known to be or acclaimed to be the scientist, the most well-known scientist today in the world. It took a genius like Newton to first question as to why would apple always fall on the ground and not go up. And the outcome of this fundamental question took him to this very famous relationship, which we all call the law of gravitation. When Newton actually discovered this law of gravitation, he didn't know that someday many countries and many scientists and organizations would use it to defy and then go to the outer space. Either a voyage with man in it, or simply to throw and put a satellite on the geostationary orbit. This is just one example. There are hundreds of examples where we'll all find that this law of gravity is the foundation stone which actually allowed some very fundamental knowledge to be gathered, and more importantly to be applied for the benefit of mankind. One of the Swamijis at the beginning, Maharaj at the beginning mentioned the famous exploits or predictions of Bharadwaj, Muni Bharadwaj, and subsequently what Purkare also showed, and so on and so forth. But the chronicled history tells that the first ever man-made design of an aircraft was due to Da Vinci. So this was the sketch of Da Vinci, which actually, in fact, story goes that he actually made an attempt but miserably failed. But it did show the importance of the aerodynamics, the need of aerodynamic stability for anything to be flying and be stable. It took 300 more years before the Wright brothers actually flew an aircraft. We all are aware of the famous discovery of Faraday, who first showed that if you create a potential difference by way of spontaneous dissociation and connect it into a closed circuit, electrons flow, and that gives the electrical current. Obviously, Faraday never had a clue as to where it is going to be used right tomorrow, if at all. Again, took more than 100 years, and took the genius of Edison, who first showed that the incandescent bulbs could be one such example of application of flow of electrons. So there are many such examples we all hear about. Today we all are so used to antibiotics. When Alexander Fleming first found the growth of such microbes, he obviously didn't anticipate that someday it will revolutionize the medical history or treatments of mankind with something called antibiotics. So science is all about the fundamental question of know why, irrespective of whether you're going to use it today, tomorrow, or even at all any day in future. So I would simply tell you that if you are pursuing science, you are essentially pursuing a fundamental question as to why. And it is true that science is all about unraveling the mystery of nature, and all our curiosity-driven acts take us to a very different plane. And majority of the major discoveries in the world happen primarily because everybody, or some of the very over-curious scientists or individuals, wanted to go beyond what is already can be seen. The next question is that, what is the use of science? So the scientists don't necessarily spell out this is going to be used in this particular application, but there are applications. That's when you enter the domains of engineering. When you apply the fundamental rules of science and make certain improvement, certain inventions, which certainly accrue benefits to the society. So that's engineering, when you offer solutions to the challenges faced by the mankind. And then subsequently, when you actually discover, invent, and innovate, and that's when you enter the domains of technology, which is a means by which the fruits of the discovery and invention can reach to the common masses, and at an affordable and ethical way. So if this is the overall scope of science, engineering, and technology, we'll soon see as to how they interlink with each other. When I say this series, you tend to believe that I'm advocating that always science, engineering, and technology follows in this order. There's no necessity. For example, here is an example when Einstein predicted the existence of gravitational wave in 1916. It took exactly 100 years for the technologists and engineers to come up with the famous LIGO, because of which the gravitational wave could be proven experimentally after 100 more years. Many of you would have heard the notion called nanometric material, nanomaterials or something, and today those even who work with micro or macro also would like to say 1000 nanometer, just because it's fashionable. But the first ever, one of the first ever exploits of nanometric length scale for engineering application was made in 1926-28, at least was predicted and shown experimentally. But the proof came 40 more years later when the electron microscope was discovered. I'm referring to something called age-hardenable aluminum alloys. And for example, an alloy which at room temperature after fabrication gives you certain strength. But if you take to slightly higher temperature and hold for a while, and then bring it back to room temperature, you get a strength which is more than doubled by then. And majority of the structural members of the aircrafts that we use today and we see flying, almost 70% of the structural members of the aircraft is made from such age-hardenable aluminum alloys, which was the strengthening of such alloys was predicted in 1928 by two scientists independently, Guinea and Preston, and that's why the particular precipitates are Guinea and Preston zones. So they were proven only after the discovery of first X-ray diffraction and then subsequently electron microscope. So after 40 years, they were proven. So many a times actually the technology also helps the science to be proved beyond doubt. So this is exactly what I was trying to say, that so science is nothing but know why, and the principal objective is to unravel the nature, and through such curiosity-driven acts, what you come up with at times is a discovery, which happens not every time you make an attempt, very rarely, and after a long time. Engineering is about know-how, and what comes out at the end is a product or a device through some important invention. Technology, on the other hand, borrows from both science and engineering, and essentially, as I said, is nothing but what sells in the market. There may be one single molecule discovered which may have a huge medicinal effect, and the engineers and the scientists together can actually produce replica of them, which can prove that all 4 or 5 of them are equally effective. But eventually, one of them will stand the test of the market and will sell in the market, and that's technology. So I just picked up randomly some of the faces which are very well known to you. I don't have to explain what Newton did or what Einstein did or even what our own C.V. Raman and J.C. Bose did. But all they did was to create a fundamental truth. But always it takes the genius of an Edison or someone like him to actually make use of those fundamental principles. And eventually some of these great minds take it to the society at an affordable and ethical way. And that is through innovation. So that's why I said that the principal thesis is science, engineering, technology, they actually form a closed loop. And at the centroid of that triad or triangle would be the society. So academia produces knowledge. In fact, I often quote this, that in an academic setup like Narendrapur or Kharagpur or Kanpur or any of these places well known for education, we primarily pursue one goal, and that's knowledge. In fact, Maharajas at the beginning also mentioned why this is so important. Today we live in an era of knowledge-driven society. If knowledge is a coin, it has two sides. And one side is teaching or dissemination, and the other side is creation or research. So academia creates and disseminates knowledge. The research organizations, they pursue invention, and the industry laps them up and translates and makes use of them to create viable technology. We all need that, and that's the reason, and this circle continues because the cell phone that you're carrying today, you tend to believe is probably the most sophisticated device one can think of. 6 months down the line, you'll find another version of that which will be much more faster and more powerful. So obviously you would request your parents to get the next version of the device. So that's the demand of the society. And this whole thing continues forever because this is how the modern innovation ecosystem is designed. And this is exactly why we need all three of them in closed loop: science, engineering, and technology. Now, having defined all this, I'm going to now share some of my experiences that I derived in this CSL laboratory some years ago. And by the by, some of you may know, it's not too far, just at the Jadavpur, the police station crossing. This institution was founded in 1950. The founding director was Dr. Atma Ram, who went on to become the Director General of CSR sometimes later. But the principal driving force behind conceptualizing CGCRI, or even I would say feeling the need of creating an institution solely on glass and ceramics. When it was founded, it was called Glass and Silicate, subsequently it was made Glass and Ceramics, was none other than Meghnad Saha. So Meghnad Saha, being an astrophysicist himself, realized that after the Second World War, there will be a huge demand for glass and specialty glass, optics basically. So that was the reason why this was the fourth oldest of the CSR in the chain of CSR laboratories. Now, let me take you to an interesting form of application of glass. And this is a glass, this yellow glass is called a lead glass. What you're seeing here is the hot cell at Tarapur nuclear reactor. So the place is meant for handling radioactive elements, create nuclear fuels, which you burn and then derive electricity out of the fission reaction. So these are all radioactive elements. The environment is radioactive, so you cannot go anywhere close to it. But yet you need an access to the devices. So the whole place is completely sealed off, and you can't even open it, even if something goes wrong anywhere in between. So it has to be so protected that there is no repair by a human being, even if something goes wrong. So you need an access, you need to see what's happening inside, so you need a window, a transparent window. And a window which will not only shield the alpha and beta rays, but also gamma ray, which is much more penetrating because of a shorter wavelength. So in order to protect the environment outside from very penetrating gamma ray, you require a glass window which is almost a meter thick, but not of a single composition. It has 5 different compositions, so 5 different layers. Now, if you have one glass sheet and make another glass in front of it, and if you have an air pocket in between, the refractive index changes. So the light from inside cannot come without distortion to the observer. So you need 5 layers. First of all, why 5 layers? Because if you make one single glass, the total thickness of the window will be so large that light may eventually get very heavily absorbed. So in order to reduce the thickness and yet not allow any change in the refractive index, you have to actually use 5 different glasses. The first of it will be a borosilicate glass, which has the highest radiation absorption cross-section for gamma ray. And at the end will be a lead glass, which is 70% lead. Now, why am I talking about this lead glass? This glass, because it is 70% lead, can be melted only in a crucible made up of pure platinum. The platinum, you know very well how expensive it is. If the project cost is 100 crore, 70 crore of that will be only to make the platinum crucible. And when this platinum crucible was to be transported from a place near Mumbai, throughout the road we had to have insurance and heavy security for its transportation because of the heavy cost of the material. And you'll be surprised that the thickness of the metal in which the glass was melted is a millimeter or less. So you actually have a refractory crucible. On top of that, you have a layer of platinum less than a millimeter. Only in that you could melt this glass. Again, the question is that why is it so important? There are only 2 or 3 countries in the world who can make this glass. And without this glass, there is no atomic energy because you cannot have a hot cell and you cannot see what's happening inside the hot cell. So if India has to be potentially a potential country producing nuclear power, then we have to have a hot cell, we have to have a window, and the window has to have a glass of this sort, and it took CGCRI 40 years to perfect this technology. Now this is what I wanted to bring to your notice. So to create one single window, you require a glass which requires an implementation of platinum technology, extremely expensive, and it took 30 to 40 years for CGCRI to complete this project. After the use of the nuclear fuel, the uranium still has radioactivity, residual radioactivity. You can't just throw it in the garbage. You can't even bury it underground. You can't even put it in your cupboard. So what do you do with it? What is the accepted principle of the society today? First of all, if you take a metal, you all know, you expose to water or some oxidizing environment, it is bound to get oxidized over a period of time. So pure uranium will convert into some other compound if it's left to itself. So you have to first capture it in such a way that it will not find its way to any other medium. So you know very well, if you go back to the material science, you'll immediately recall that the highest bonding strength usually is available in covalently bonded solids. So let uranium be part of a very strong covalently bonded matrix. And the easiest of that is glass, silicate glass. So if you replace some of the Si4 plus cation with the uranium cation, then you're binding uranium to that glass perpetually because the bond strength is very high. But glass is very brittle. So you keep it somewhere because of mechanical forces, it might disintegrate and break into pieces. So you melt molten, first you make a melt of glass, you now alloy it with the residual uranium, make it a part of the matrix, you solidify inside a metal canister, and in that steel canister, now you cover with ceramics, with cement and concrete, and then you bury deep inside the earth in a desert area, so that even if a very large earthquake with a high Richter scale vibration occurs, still, even if the wall breaks, even if the metal breaks, the uranium will never be able to come in contact with water. In other words, will never be able to leach out. In order to develop this technology, you require very simple glass particles, which again you can't go anywhere close. So you have to feed it inside a chamber, which will melt. For feeding and flowability, you require glass particles, which are very fine and will have exactly the required borosilicate composition. So this was again perfected by CGCRI. The demonstration was done, yet not made into a technology form, because there was nobody willing, a laboratory like CGCRI cannot be all the time supplying such glass particles to another organization. So this has to be done by an industry. So despite the proven technology, nobody came forward who would wrap it up and then take it to the industry scale. eventually we succeeded, and today there is a particular industry in Mumbai who actually does it routinely and supply to atomic energy. It took again more than 10 years to be able to convince that company that you have enough profit for taking it to the commercial stage. You would have seen this high tension lines. If you go just few kilometers away, you'll find in the distant land over the paddy fields, the crop fields, you'll find large poles and the electrical wires hanging between the poles, and that's how you transmit electricity. You may be generating somewhere in Purulia or Bankura, or maybe Golaghat, but you take that electricity to several hundred kilometers away, and you transmit through such lines. Now these are metal wires. Obviously you'll use a metal because metal has no band gap and highest conductivity. So let's say aluminium or copper wires, and if you keep pure aluminium or pure copper wire hanging somewhere in the middle of a distant field for a long time, over a period of time, if you keep monitoring the length, you'll realize that the wire length extends, and that's through a mechanism which is called creep. Deformation under constant load at an elevated temperature. This elevated temperature is not much, I mean maybe 30, 40 degree or 50 degree at the most, but even that is enough for the wire to extend over a period of time. And if this extension continues continuously, then at some point of time it's going to snap. So in the middle of the night, transmission from South Bengal to North Bengal stops, and you don't know where it has happened because the line is several hundred kilometers. So you need a monitor which actually will constantly monitoring the length change over a period of time and keep feeding the data. You cannot use an electromagnetic device because this is very high electrical current carrying conductors. So you need a device which will measure the length scale change by less than a micrometer, so precise, and is not going to be affected by the electromagnetic field. The only way you can do that is using an optical device. And this is an optical device, this is a small optical device here, which actually can measure such length change variation very precisely and continuously. This is made of optical fiber. And this optical fiber device is used for so-called structural health monitoring. This similar device can be also used for your railway bridges or road bridges, even a 20-story tall building. Very soon Calcutta is going to get the tallest building in India. So to keep monitoring the length scale change and ensure the structural health of such structures, you need a device, something like this. So this was developed by CGCRI. Out of what? Optical fiber. Today, I'm sure that all of you would have heard the utility of optical fiber. So what is this optical fiber? Just a hair-like thin, few tens of a micrometer diameter, thin wire. So how do you produce them, and why these are so important? Because all the network that we use today for mobile, for internet, and so on, a large part of that is actually based on optical fiber. So how do you produce optical fiber? It's basically, imagine a glass tube with a hollow core. So you have a core which is hollow. Now you deposit certain oxides on this inner core and heat and pull. So when you heat and pull, you expect the diameter to shrink, and eventually the diameter will shrink in stages, and that's typically what you call extrusion. And you start pulling, so much so that from a few centimeter, eventually you pull it into a thin wire of, let's say, 10 or 15 or 20 micrometer. And within that 20 micrometer, you have a 2 to 3 micrometer diameter concentric tube, which is now solid, no hollow, but has a different refractive index because you deposited certain other oxides other than silicon. So these oxides, because they have different refractive index, will ensure that the light you launch from one end never escapes because of the total internal reflection. So this is how the optical fiber works. So this is a technology which is not done, I mean, CCRA is not the inventor of glass fiber technology, but CCRA is the only lab in the country which has developed at least 3 possible devices in the recent past. The optical amplifier, which is used for amplifying the signals for all the mobile and internet network, the structured health monitoring device, and then finally a super continuum source. Now, I'm using a laser pointer, and this is so useful because it has single wavelength and it's convergent and goes parallel, but has a single wavelength. If you have a similar laser with multiple wavelengths, which is true for a huge band of something like few hundred to few thousand nanometer, so that means you are covering the entire wavelength band of infrared to optical and beyond. So in such a source would be called a supercontinuum source. So this was also developed and given to the industry by CGS. Again, it took multiple years before this can be actually translated. Here is an example which I find should actually send a different message to all of you. First of all, what I'm talking about is an artificial hip joint and knee joint. So, for those patients, need not be always aged, even some other unfortunate individuals may need a replacement of knee or hip joints. And this is a ceramic and this is a metal part. So metal to ceramic is always a very difficult because of the high level of wear and tear. So this was developed by CGCRI through a scientist who is here receiving an award, Dr. Devabrata Basu, who is no more. And he died at the age of 50 plus years. And Dr. Basu always carried a very major ailment because of which he had to take a dialysis in his own lab. So before he died, for the last 10-15 years, he had to take at least one dialysis every day sitting in his own laboratory. With a single-minded devotion, he developed this implement which was given to an industry which were able to sell it at a price of 25 to 30,000 rupees a piece. The same device marketed by a multinational company from USA at that point of time would cost anything from 1.5 to 1.8 lakhs. So 5 to 6 times costlier than the device created by an Indian laboratory. These devices were implanted into more than 100 patients. I'm talking about some 5 years ago. By that time, already more than 100 patients benefited. In fact, one of the patients, this gentleman is a retired employee from a public sector company, came personally to thank CGCRI during my time and said that he was absolutely elated by using this device. And these operations were conducted by this gentleman called K.H. Sanchetti. Those of you who ever visit to Pune would come to know, he is considered to be one of the most famous orthopedic surgeons in the country. He used to be the personal physician of the President of India. So he came forward and then he did all those operations. Now, look at the devotion of the individuals who pursue science and translate science into a product. Dr. Basu, he didn't get a lot of money. He in fact gave the patent to the laboratory, and the laboratory transferred it to a company, and the company made those devices. So this is a big question mark, that even if a device which costs 5-6 times lower than the one which is marketed by a multinational company, why is it that, and proven already that they are useful, why is it that still the society tends to believe more the multinational companies than the innovations at the laboratory? The answer to a large extent lies in today's world, which is so much enamored with the commercial marketing strategies and so on and so forth. So, I mean, this is where we scientists and technologists tend to feel very frustrated, but this is a question which needs to be answered. So so this is one more example where this kind of an arsenic removal plant. Many of you, particularly in this part of the country, you are aware that arsenic is a major evil, and a lot of people get arsenic affected because of the groundwater pollution. So this is a device which actually can purify water more than 30,000 liters per day, and is a community level device. Able to take it to the market and to be able to take it to the society is a very, very difficult task. But this was also made possible. And one other example, you'll be surprised to learn that there's something called Ukrainian clay. And this the discoveries are not necessarily always made by highly educated scientists. This was an innovation, simple innovation of by a particular treatment of a local clay. Our scientists at Naroda Center could create a substitute to Ukrainian clay and make certain tiles out of those. Forget about all those details. Look at these numbers. So the import of that particular clay used to be almost 12,000 million tons, which got reduced to hardly 1,000 or 2,000 tons. There were only 14 units in 2005, and which rose to 64 units in 2011. The profit margin increased by 6-fold. So a single micro-scale company, which was earlier, let's say, making 1 crore profit a year, now started making 3.5 crore profit a year. So profit margin increased by 3.5 times. By a single innovation, very simple innovation by some of the laboratory staff of CGCRI. So this innovation also is equally important to the society as much as a paradigm shifting scientific discovery. Now, the organizer already has given me an hint that I've run out of time, but I was very keen to talk about this initiative of Government of India, which was launched at the Rashtrapati Bhavan in 2015, called Impacting Research, Innovation and Technology, or IMPRINT. And it's all about India's own version of grand challenges. You're aware of grand challenges launched by US, where they defined these 14 grand challenges faced by the humanity in this century. We decided that in India, we don't need to follow the American model simply because the society is not at par. Our basic datum is not at the same level. So we thought we would first address our own challenges, and we defined them into 10 domains. And for example, energy is one of those domains. And these are the themes and the domain, and this is the overall objective of energy security for the country. And why this is important is because if India needs about 330 gigawatt hour electricity for its sustenance, 60-70%, two-thirds of it comes from fossil fuel, hardly 10-15-17% from the renewable resources. Hydro is hardly 13-14%. So this is the trend today. Now, if you look at the global scenario, India is the third largest consumer of electricity. But look at the gap. If this is what China consumes, this is what US consumes, India consumes about 1/4 or 1/5 of that. But if you look at the per capita consumption, we are the second largest population, so please don't forget. So per capita consumption wise, we are minuscule, even way below than, certainly way below than Japan, US, China, or Germany, even lower than some of the Scandinavian countries. Now, consumption wise, almost equal amount is required for industry as we need for heating and cooling our homes in the domestic purpose. So this is the overall description of different sources, and these are the pie chart which tells you that the bulk of it is coming from coal. So we are hopelessly devoted to coal. What is going to happen after 20 years? Now, if it is, let's say 2015 is the datum, 20 years hence, Brazil will require slightly more higher amount of energy. So the increase is 40%, not so small. Russia is almost saturated. US is almost saturated. China will require some more. So China, Brazil, and now look at India. So the generation, if it is 330 gigawatt hour today, we need easily more than 1000 gigawatt hour from 20 years from now. So who will give so much of energy and where will it come from? So the prediction is that India will need a lot more energy generation from the renewable resources, a lot more from nuclear, more than 300% than what we are doing now, and also, but will still be dependent on coal to a large extent. If nobody knows how much coal will be left with after 20 years. So the global consumption of, so the global share of India's electricity generation will be despite so much increase, will only be 9% of the total world's consumption. Whereas China will actually produce and consume 25% of the total capacity of the world. So if we really want to catch up with China, 15 years ago, China was chasing India. And today, this is the large gap that we are facing. So who is going to solve these problems? So Imprint was all about that. So these are the overall themes. Look at this particular objective. We said million challenges because 10 domains, 10 themes, in each domain 10 themes, 10 topics, 10 titles, makes it 10 raised to 4. 100 variants, India is a large country, of each makes it 1 million challenge. Now that's very daunting, but who is going to solve them? We said million challenges but billion minds. So they were synergistic with other initiatives of the government, and the Prime Minister at the launch said, science is universal, but engineering must be giving local solutions. So that was our motive. So we actually launched all over the country. 2,612 proposals received and reduced from 200 institutions, 608 participating, and more than 5,000 individuals wrote proposals. So went through various rounds of screening, 259 were selected, and eventually 142 are underway. Now, you must realize that, I'll go to the next one. So this was Imprint 1. We are now into Imprint 2, and several rounds of Imprint 2, 2A, 2B, and 2C. What is that we are trying to do? So this is a national initiative, first of its kind, because of 3 reasons. It's for the first time we are talking about the entire engineering challenges of the country, not one solar or one water or one transportation problem. We are talking about all the engineering challenges faced by India now and in future, divided into 10 domains. First reason. Number 2 is, this was a first initiative when all IITs and ISC and all top institutions came together to actually take care of these issues, these challenges. And number 3, and the most important, this is an initiative where we are talking only about translation. So now I'm taking you back to the first slide I showed, the need to have interrelation between science, engineering, and technology. We say that all of us are producing knowledge, so that's our job. But what happens to the knowledge? Who makes use of them? Imprint begins where knowledge is created, to take it, to translate it into a viable technology. And so I will end saying that in this little half an hour time, I tried to bring before you, for all of you, to actually, what your Principal Maharaj said in the beginning, to develop a temperament which allows you not only to raise the fundamental question of know how, know why, also not enough to say know how, but also reach a stage where you're able to make use of the fundamental knowledge, translate them into a viable technology and product for the benefit of the society. So science is pursuing the truth relentlessly, regardless of its necessity and immediate scope of application. Science provides clues, if not answers. Science extends as far as imagination goes. Science never fails, but scientists can. Engineering is all about enabling and providing solutions borrowing from the fundamentals of science. And technology is the last mile for societal benefit based on scientific discovery and engineering inventions and innovations. So let us ensure that science, engineering, and technology in India complements each other, not competes. and flourishes so that our society soon attains the desired growth and prosperity. And by the virtue of, by being senior to you in age, I take the advantage of saying that if India has one unique resource and strength that the entire world envies, that certainly is the demographic dividend, the youth, you. So the future of India lies in your hand and intention. So with that, I'll close, and I'll be very happy if now or later, if I can answer to some of your questions. Thank you very much.
Wonderful, a perfect, picture perfect lecture you have heard. If you have any questions, please ask, very quick, because we are running out of time already. If you have, otherwise, please Sir Vikramjit Basu, please come. We are going to felicitate Professor Manda, and Vikramjit Basu will felicitate. Thank you very much. You are welcome. Yes, yes. This will have no. Okay, thank you very much. At 2 o'clock, sharp at 2, we'll start again. Our start.
Students, a small announcement for you. So, the time, the stipulated time, you please kindly follow the time stipulated what is mentioned. And one more thing, now you just you maintain your line while going out of this hall, and there on the just below the staircase your lunch will be served, lunch pack will be served, and you will be asked specifically, categorically where you have to go and take your lunch. That's the first thing. And one more thing which is very important, that while you are coming down, I will call group wise a few of you, not the entire group, 2 or 3 groups I will call. So we'll have a very small photographic session. So as many as possible, we'll have a photographic session with all our dignitaries present over here today. So now it is the lunch time, and please maintain the stipulated time for the post-lunch session, and we'll meet here. Thank you. And you please go out of this hall through that door. It will be open. I request someone to please open the door, and the teachers and the mentors who are here with the students, kindly maintain this.
I am profusely apologetic for half an hour late for insurmountable reason. I'm really sorry. Now Professor Tanushree Saha Dasgupta will deliver you a talk, and her topic will be on computational science and nanotechnology. Understand? She will now deliver a talk.
Can you all hear me? Yes. So what I'm going to talk about is, it's a change of gear. You have heard from Professor Manna about the technology. So what I will talk about were the use of basic science and the basic knowledge which may be useful for understanding some of the things of the technology. As Professor Manna said that you really need science to be connected to technology. So you need the basic science for getting your knowledge delivered in a form which will be used for application. So one of the things in this context he also mentioned is that of the nanometric. And what I am going to talk about is materials when you make them smaller and smaller and get into nanometer length scale, and suddenly properties change. And I will try to kind of educate you to this domain. It's just an introductory talk. So if it gets yourself motivated in this domain, there's lots of opportunity both from basic science point of view and application point of view. So title of my talk is Properties of Materials at Nanoscale, and there is a small subtitle, First Principles Perspective. I'll also tell you what that these words mean, because for you it probably means nothing. So it will be my job also to explain to you the meaning of this subtitle. At the moment I am affiliated to two of this institute. Which one is the pointer? That's I think dead.
The middle one, the round one.
Yeah, it's dead. Even if you have a speak, it's fine. Yeah, it's not working. So at the moment I'm affiliated to two of the research institute. So some of you, when you grow up and take the path of doing research, you may come to any of these two institutes to do your research as a PhD student and maybe later on as a faculty. So one is S.N. Bose National Center. It is in the name of Professor Chaitendra Bose, in whose name half of the fundamental particles of the world are known. How many of you know the name of bosons? I see one hand, two hands, three hands. They all know. So you all know the name of bosons, the fundamental particles. It is in the name of this Indian scientist. It's great that half of the fundamental particles are dictated by one Indian. And the other one is the Indian Association for the Cultivation of Science. This is also very famous. The single Nobel Prize which India has got in the field of physics has been given in this institute. So both these institutes, as you can see, both are in Calcutta, and they actually have contributed a lot to Indian science. And I'm very honored to give this talk in this stage because Indian Association of Cultivation of Science was actually founded by Dr. Mahendralal Sharkar, who was a great disciple of Ramakrishna, and it feels great to give this talk, which is arranged and organized by Ramakrishna. Well, and these are the pictures of these two places. Now we start with materials. It's actually an understatement to tell in front of you the importance of materials. The impact of materials in human civilization is so much so important that ages have been defined just by the name of materials. To start with, you have the Stone Age, a material, Bronze Age, a material, Iron Age. So ages in human civilization are just named after materials. And we are in the age of silicon because everything is governed by your silicon industry. Leonardo da Vinci, how many of you know of his name? Everyone. Who was he? He was a famous painter, but he was also a philosopher with a great scientific mind. I think it was also also said the scientific mind, the scientific attitude. That's very important. It's not about science, how you live. Science is a living, how you think. That is very, very important, which was mentioned in your introduction. So what he said, the coming age is going to be an age of designed materials. What does designed materials means? This is the quote from Leonardo da Vinci. You can't read it, so I'm just reading it for you. When nature finishes to produce its own species, man begins using natural things in harmony with this very nature to create an infinity of species. How can we make new materials which can be applied to industry, which will have a great application possibility? In that way, we'll make new materials. Or the known materials, we will come up with new functionalities of these known materials. And to do that, you actually need a handshaking between experiment, simulation, and theory. So in this world, science is no longer a game of an individual. It's a teamwork. We really need to team up. That is a modern science, where you have a cross-talking between experiment, theory, and simulation. And that gives rise to this branch of science which is known as computational material science. Even before a material is synthesized in the lab or its property is measured, you do computation, you tell about the properties of these materials which are yet to be synthesized. Or you provide a reason why a material is behaving in this way and not in the other way, giving rise to an understanding. And one of the sub-branch of this computational material science is calculation of electronic structure. What does that mean? That if I give you a material, I tell you its composition, what it is made out of. Is it made out of copper? Is it made out of zinc? Is it made out of carbon? This is called composition. And I think also Professor Manna mentioned a word called alloy. Alloy means where you make combination of these different elements to give rise to a composite thing which has, let's say, a fraction of carbon, a fraction of boron, and a fraction of iron. Like you know a steel, that's an alloy. So you need to know the composition. Then you need to know the structure. How many of you know of the word called lattice? Everybody knows it. So lattice is a periodic arrangement of these atoms, right? How you arrange these atoms. So therefore you need to know of the structure. Are they arranged like in a FCC lattice, BCC lattice, or maybe much more complex lattice? So once you know these two things, the third vertex of this triangle is the properties. I know the composition of this material. I know the structure of this material. What will be the properties it will show? And as it looks like, many of the properties of these materials actually depend on the electrons. Electron is the glue that basically binds the atoms. So many of the properties of these materials are dictated by the bonding properties. As a result of that, to connect these two vertices to the third one, the calculation of the electronic structure becomes so important. Now, I talked about materials, but I promised you that I will talk about nanoscale. The materials becomes even more interesting when you put them at the nanoscale. So what is a nanoscale? How many of you have heard the word nanometer? What it is? How do I connect a meter to a nanometer? 10 to the power minus 9. Everybody knows. So what I have put here is to just, I don't know how well you can see it because it looks very, very faint to me. But what it is shown is the size of a bee 2.5 centimeter. Then you have like a red blood cell. Already we are at the length scale of micron. You make it even smaller, like a carbon nanotube. That is one example given. And look at the radius of this tube. That's like 2 nanometer, where we have come across already at the nanometer scale. So we have heard about atoms and molecules. We have also heard about condensed matter systems, like this bench, like this laptop, its screen. These are all condensed matter systems, where I have talked about this lattice, the periodic arrangement of the atoms, which are going to the macroscopic scale. So I can assume they are actually going to infinity until I really reach the edge. But the bulk of the material is much more than this edge effect. So I can actually kind of neglect that until unless I'm sitting at the edge. So this is a condensed matter system. And the nanometric world lives in between atoms and molecules and the condensed matter system. So they, as I mentioned to you, exhibit unique, novel, tunable properties which you can't find in their bulk counterpart. And there is a tremendous progress in the experimental technique. High quality samples have been made, which made this field really a field of much excitement. So there is an important branch of physics that's called mesoscopic physics. It deals with physics of small condensed objects, hence a collection of atoms, in contrast to atomic physics or molecular physics. I have hundreds of atoms, tens of hundreds of atoms, not one atom. And these objects are often in nanometer size regime, giving rise to this word, the nanoscience, and the mesoscopic physics, which was actually some time ago when people didn't come up with the word nanoscience, was used the word mesoscopic physics. This is kind of a sub-discipline of this nanoscience. And this nanoscience is an interdisciplinary science. I'm a physicist by training. You will find many of the chemists working on it, the biochemists, and also the engineers like Professor Manna, who will be also working in this field. So this is a playground where everybody can join and participate. So what makes this very, very important, going to the nanoscale, I said that the properties change quite a bit going to the nanoscale. And the one important effect is that comes into play when you make the system smaller and smaller is that of the quantum confinement. So you take a bulk material, which is a three-dimensional object. So these boundaries are really moved to infinity. So they are really large. From bulk, you can go to thin film form, where you already make one of the dimension much smaller compared to the other two dimensions. You can reduce it further, make it one-dimensional, like a nanowire. That means it is confined in two of the dimensions, and in the other dimension it is actually free. You can even go to the extreme case, which will be like a large molecule. Some of you have heard about the word like a buckyball, one form of the carbon, which is spherical and consisting of many of the carbon atoms. So that will be like a zero-dimensional, because I am confined from all three directions. And the moment you confine this material to such a small length scale, what becomes very important is quantum mechanics. We all know everything will be quantum. If you cool it down to very low temperature, close to 0 Kelvin, I will see all the quantum motion of the electrons. So what is interesting in the nanoscale, such kind of the quantum effect you can see even at room temperature. So that makes it far more exciting. So what is shown here, I will not explain to you because I think you still need to mature to understand it. But what is shown here is a behavior of the electron, which is made in this plot, which is the energy of this electron. Plotted here is the states that are available to this electron. So when you are in the bulk regime, this dependence is kind of parabolic. So this electron is really free to move. When you are in the thin film limit, as I said, already one of the dimension is confined. So in one particular direction, the electron doesn't have that freedom, but it is really confined. And what you see that this parabolic nature now becomes like a step function. If you are gone to a nanowire limit, you see that shows even something which kind of diverges. You can see it very clearly here. You go to a quantum dot regime, all you have is just levels. You no longer have something which was parabolic. This is what is non-dispersive. That means this is a straight line. This electron is really confined in a level. It has become like an atom. In case of atoms, you talk about really energy levels, while you, let's put these atoms and make it a crystal like a semiconductor, you talk about bands, the valence bands and the conduction bands, where the electrons really move in all this and between all these energy levels. So this is like a band, while this is like a level. So the same material, whether you are in the bulk limit or in the quantum dot limit, there is a very big change in its electronic structure. Now you may say, so what? So what? You can see that going from a bulk to the nano, you are basically changing its optical property. Why it is an optical property? The reason you see really some material having some color or a different color is because which wavelength is getting absorbed in this material, and that is dictated by the optical transition of this electron from one state to the another state. So it is remarkable, you take the same material, you just change the size, so size was reducing in this direction, you just go from red to blue. So the color of a material changes remarkably if you make them smaller and smaller and get into the nanoscale. That's a fantastic thing. It is just not those drawing, but you can see it in your lab just by doing the experiment. Now the three pillars of this nanoscience and technology. First is the manufacture and manipulation, and there can be two different methods, either top-down or bottom-up. Then comes the characterizations, imaging by imaging and probing this material. The third one, which will be actually our focus, is the theory, modeling, and simulation, predictive computation of its properties. Now, what are these computational science? What are these computational aspects? It uses basically the capabilities of computers through methodologies of scientific computing to solve some scientific or engineering problem across all disciplines. I'm specifically talking about computational nanoscience, but it can be in any branch of science. Uses heavily on the advances in applied mathematics, because mathematics is the language, as we have learned in the talk by Professor Malli. And computer science uses numerics, graphics, and etc. So it draws heavily on the advances of those fields. Contributes to the emergence of the data-intensive scientific inquiry. I will come to that. Now the scientific paradigm, how the things have changed over the years. 1,000 years ago, science was completely empirical and observational. You observe something and then you try to explain it. Right? Few hundred years ago, the theoretical branch emerged where people tried to put mathematical formulation of those observations. A decade ago, computational branch emerges. You can simulate the phenomena in your computer, which you actually see in nature. So this is a technology-driven branch of science, and It of course depends heavily on the use of computer. All of you are having server or desktop machines that you use. All of you now have either in your school or even in your home. What is used primarily in such kind of doing science are the high performance computers. So high performance computer, I just tried to show you a picture of it, where you have several of these CPUs. They are put together, hundreds and thousands. In this particular case, this was about 3,000, close to 4,000 such CPU, and you make a link between them so that they can talk to each other. That means a given job is kind of distributed among such 4,000 processes. And what is shown here is the capability of this machine, the particular machine, that is 75 teraflops. So how many floating point operation per second this computer can do, that is measured by this unit called flop. You can see it's teraflop and 75 teraflop. And this is nothing. I mean, these days, these kind of machines are available even in many places in India. So this is the kind of the compute power that is needed, or the advancement that has happened in your hardware, which can provide such kind of computing facility. And this is basically the high performance computing and the Moore's law. And according to him, that this is measured, the computing power, as I said, has been measured in terms of flop operations. And this is one petaflop machine, and this is as a function of year. And even in India, with the new initiative of National Supercomputing Mission, now we are getting petaflop machines in India. It's like a government mission that has been taken. So computation has become so important, government understands it, and it has put a lot of money in making such kind of petaflop machines. And at the moment, there are at least 2 petaflop machines that are available in India. Now let's come back to what I started with, which is a computation of electronic structure. If you take a material, if you break that material into pieces, what you will get are some atoms. If you break that atoms are made out of electrons and ions, or which is neutrons and protons, and you can think that you have some valence electrons, so therefore you can consider it as a combination of electrons and ions. Now, how do I solve this problem? Because in this material, there are many number of these atoms. So therefore, there are so many numbers of these electrons and ions. And each of the electron, by electrostatic repulsion, they are interacting with each other. Each of the ions are interacting with this electron because they are attracted to each other. And each of the ions are interacting with each other because they also repel to each other. So how do I solve this problem? I know what are the quantum mechanical forces acting between these electrons and ions. I just don't know how to solve it because they are typically 10 to the power 23 in number, and I can't solve them. So therefore we have to do approximation. So the first approximation that have been done is that the mass of the electrons and the mass of the ions are very different. The ions are much more massive compared to electrons. So as a result of that, since the electrons are much less massive, they are moving much faster compared to ions. So which means, the first approximation, I can deal with the time scale associated with the motion of electrons and ions as separate. What does that mean? I can assume that the ions are static objects in the plane when the electrons are moving. So I think I do the problem like a snapshot thing. One snapshot, I have all these ions static in one position, and that creates some kind of a field in which the electrons are moving. I solve that problem. Then I do the next snapshot when the ions have moved a little bit, and I have in that kind of field solved again the electrons. So that is the first approximation, which is known as a Born-Oppenheimer approximation. You don't have to remember the name, but just remember that the ions and electrons are treated separately. Even after I have done that, I have done away with the ions. They are considered as static. They are not moving at all. But I am still left with so many numbers of electrons. And then what we do is a one electron approximation. What does that one electron approximation mean? I take one electron out of this crowd, like myself, and distance it from others, like I have done.
No sound, man.
No sound? Sir, I can't see you because this projector is so strong, I can't see any one of your face. Can you hear now? So you always need the microphone.
You have to keep nearer to the microphone.
Nearer to the microphone. I thought I am very loud. Is there...
Just go to the corner and then you can see the
corner?
Yeah, go to the corner of the podium and then you can speak from there.
Your advantage was you were at least double my size. Hi. Hi. How much you could hear me? Nothing?
It's absolutely all right.
More than enough. Okay, so I was talking about the approximation, and I was talking about two different approximations to solve the problem of many electron and many ion. So the first approximation I talked about, since electrons are much less massive compared to that of the ions, you can treat them separately. So that actually simplifies the problem quite a bit, because now I have to solve only the problem of electrons, although they are many in number. Now the next approximation that we do to handle with many electrons is I isolate one electron out of that so many number of electrons, like I have done myself. I am standing on this stage and I replace all of you, which are the rest of the electrons, by a homogeneous field, and I just interact with that homogeneous field. That means I don't differentiate whether Professor Malik is there, Professor Manna is there, or Bikramjit is there, or you are there. For me, all of you are just audience. And that is exactly what is done in this approximation. You take one electron out of the crowd and replace the rest of the crowd by a homogeneous medium, so that I don't have to interact with each one of you individually. I interact to all of you collectively. That is the second point of the approximation. And these two approximations led to a very famous theory, which is known as density functional theory, for which Walter Kohn was given the Nobel Prize. Because you can then handle the problem of the electronic properties of the materials and can compute it. It was a major breakthrough. Just to impress on you, these two papers based on which this theory was made, what is shown here are, one thing was the citation. Suddenly it started working. The citations are already huge, and the number of publications that have come out, that have been published, the number of papers, it is showing an exponential increase with time. It's really a major breakthrough, and most of the computation of properties of materials are based on this theory. So that is the basic concept which I have already told you. You have a collection of electrons, you isolate one of them, put them out of the crowd and replace it by a medium to which this single electron interacts. So how much time I have? Near to the time. I will close with showing just one example so that they can get to the flavor of it. That was about cadmium sulfide nanocluster. Cadmium sulfide is a semiconductor, and if you make it smaller in size and get it to a nanoscale, what exactly happens? So I will not definitely have time, neither have you the background of the audience to explain all the details, but will just tell you what exactly the computation can contribute in such a kind of problem. So this is a direct gap semiconductor, as I have already mentioned, and the nanoparticles of this material can be synthesized rather easily. The situation becomes complicated because the structure of the material of this cadmium sulfide, which is there in the bulk, doesn't seem to be the same when you reduce the size of the material and get it to the nanoscale. So it can actually exist in 3 different phases, and it looks like that when you make them to the nanoscale, a combination of 2 different structures appears, and the experimental situation is rather complicated because one experiment basically suggesting it appears in the nanoscale in such kind of phase, while the others appear in different kind of phases, and there are lots and lots of this experimental result. Therefore, making the situation rather complex, because experimentally it becomes very hard to really detect that when I go to the nanoscale, whether one structure is a stable phase or the other structure is the stable phase. So, particularly in this kind of situation, computation becomes really important. So what are these 2 structures? So you have 2 elements in this material. You have cadmium and you have sulfur. So one of the structure is called a Woodside structure, and the other structure is called a zinc blende structure. In both the structure, you can see the red ball is surrounded by 4 of the blue ball. The red ball being say cadmium and the blue ball being the sulfur. Same is the case for the zinc blende. The only difference is in their stacking. Here the stacking is like A, B, A. On the other hand, here the stacking is A, B, but then you have another one which is C and A again. So therefore the stacking in one case is A, B, in another case is A, B, C, A, B, C. Is there a question? I can only hear some murmur. Anyway, so how do you build this cluster in computer? You have to build a cluster in computer. You don't know how it grows in experimental situation. One situation can be, you start with a cadmium atom, then you put as a neighbor of it the sulfur atom, and then from each of this sulfur, you again add some of the cadmium atom at this neighbor. That's a one possible way of making this cluster. In this case, if I start with one cadmium, and if I stop in the second cell, it will be surrounded by sulfur. If I stop in the third, it will be surrounded by cadmium, and it will go on like that. The other possibility is I take a cadmium sulfide like a dimer and start from the middle of this cluster, of this point, and grow it. In the first case, you have to be careful. In the first case, the cluster that I will build in the computer will be a non-stoichiometric cluster. What does that mean? I will not have same number of cadmium and sulfur atoms. In the bulk, I have same number of cadmium and sulfur. But when we go to the nano cluster, and if I start building up this way, I will not be having same number of cadmium and sulfur. If I start from the bond, then of course I will always get same number of cadmium and sulfur atoms. So you see, depending on how I am making this cluster in computer, either I get a stoichiometric cluster having same number of cadmium and sulfur, or I have a non-stoichiometric cluster, therefore having different number of cadmium and sulfur. Either it will be cadmium rich or will be sulfur rich, depending on how many shell I am going through. That is exactly what is shown here. Here, for example, I have, let's say, 1 cadmium surrounded by 4 sulfur. So this has more sulfur compared to cadmium. I go to the next shell, which is shown as shell number 5, this was shell 1. I will again have more number of sulfur compared to cadmium. So I can generate many such things like that. Yes, I will stop here. So what is shown here is the energy of this cluster as I am increasing them, growing them shell-wise. If I grow them shell-wise, what I find, first of all, their energy is not decreasing monotonically. The energy will be decreasing as I am increasing the size of the cluster, simply because volume to surface ratio will decrease as I am increasing the cluster. It costs me energy to make a surface. So therefore surface energy gets reduced, therefore the energy is getting reduced, but it is non-monotonically. And what I find, what is shown here, zinc length or Woodside, in one case this triangle is below the circle and it alternates as I am moving along this size, increasing size of the cluster. Since my time is up, I'll just finish by saying the word that when I'm creating a surface, which is more so showing here, this atom has 4 neighbors, while this atom doesn't have 4 neighbors, it has only 1 neighbor. So it is missing 3 of its neighbors, which are called the dangling bonds. It is a hand holding, so it has to hold hands with 4 friends. It could hold hand, only 1 friend, and 3 of these hands are just dangling. And that is called the dangling bond, and that costs energy. We are very happy when we hold hand with a friend. If we cannot hold hand, we are unhappy, which means increase in energy, and that is called the surface energy. So the thing that it happens is all because of the nature of how many number of dangling bonds I have, and therefore it is only the variation in the surface energy that causes such variation. Therefore all it says, whether my cluster is cadmium rich or sulfur rich, it has an effect on the number of such dangling bonds. As a result of that, depending on the experimental situation, whether they are making a cadmium rich cluster or a sulfur rich cluster, I see either they are getting stabilized in one crystal symmetry vis-a-vis the other crystal symmetry. If you want to learn more, if you are interested about it, I will be free to talk to you, and I think my email address is with the organizer. You can always drop me a line and I will be happy to talk and discuss more with you. Thank you very much for your attention. Email?
Yeah.
Very simple. My name, t.shahadasgupta@gmail.com. Nothing can be simpler than that. It's my name.
Thank you very much, ma'am. So we invite questions. If you have, please clear your doubts. Quick questions and quick answers.
That portion of the graph suddenly increasing?
Increasing.
Going up.
It is here. It is becoming more negative.
No, that why is it not decreasing perfectly monotonically? Why is there sudden deviation there?
Yes, so that's exactly what I told you. This is like not monotonically decreasing, it is decreasing, but it is like in a zigzag fashion, right? It is in a zigzag fashion because this number of dangling bonds, it varies between this and that. Precisely because of that, there in the surface energy plot also, which I have not shown you, you have such a kind of a zigzag thing. I didn't have more time to explain it. Yeah.
Please come up and felicitate. Please give her a big hand. Very much. Thank you very much.
Okay, good afternoon everybody. So what I'll do, like Professor Saad Gupta has already changed the gear, I'll further change the gear to biology and engineering. So as you know that I am a trained engineer, but for last 1 decade or so I have been doing research at the interface of biology and engineering. So what I'm going to do in next half an hour, 45 minutes is that at certain point of time I'll show you or I'll provide you certain information which you already know from your classic textbook, but I'll show you further that knowing that basic information what we have done in our research over last 1 decade or so. So you know that human body, so that there is hierarchical organizations of human body, and then smallest unit is the cell. So cells, when they form, they grow into tissues, then tissues to organs and organ systems and so on. So that has been shown here very nicely. If you see inside the cell you have DNA, and then after the cellular level you go to the tissue level, and for the tissue level, for example, this is a cardiac tissue, right? That is very important because the functionality of cardiac tissue actually maintains the heart functionality as well. And then its organ level, it's a complete heart. So heart is that much at the topmost level in the hierarchical organization. You also know from your basic biology textbook that how does an eukaryotic cell look like. So there is a difference between eukaryotic cell and prokaryotic cell. Eukaryotic means truly nucleated cell. And therefore, in this particular eukaryotic cell, what you see here, it's a nucleus, it is enclosed in a well-developed biliary membrane, and also the cell membrane is also, there is a biliary membrane. And this cell layer, that what is the cell membrane I call, so this cell membrane is not very simplistic, but it has several voltage-gated calcium and potassium channels, sodium potassium channels and calcium channels. They control many of the cell functionality. So, and there are various other organelles in the cellular system, in a cell that you already have read in your textbook. And cell is defined as kind of self-contained unit capable of replicating itself given the proper nutrients. Now, in the next level, as I said, that when, for example, in the muscle tissue, so the cells which form tissue is myoblast cells. So myoblast cells, they determine themselves to form a muscle tissue, and in this process they proliferate, means they grow in numbers. Then they align themselves in a particular manner, and then once they align themselves, they fuse and differentiate. Differentiation means differential gene expression. So in the cells, their genes are differently expressed. That is the process called differentiation. And then they mature, they form a muscle tube. And that is the way these muscle tissues are formed in the human systems. Now, coming to the more engineering interface, if you see, these are the two basic examples I'm showing here. One is the total hip joint replacement. So many older persons, they often fall and then they break their hip, and then if they have to undergo certain surgical operations, this hip joint, total hip joint replacement is one of the options. And this hip joint, this total hip joint replacement, if you see, this is the hip stem part, and here is the femoral ball that goes inside into this acetabular head, and this entire system is a very classic example where three different type of materials they are used. Typically, the stem part is made of the titanium alloys, titanium 6, aluminum 4, vanadium, or stainless steel. Now, if it goes to the femoral head, then then it is made of the ceramic. And then if it goes to the acetabular head, that is the top part, that is the polymeric materials, which is nothing but ultra high molecular weight polyethylene. So you must have heard of the polyethylene. So polyethylene is one of the polymer. Depending on the molecular weight, you have a low density polyethylene, high density polyethylene, ultra molecular polyethylene. This molecular weight increases. So in this particular case, you know that there is a significant opportunity to improve the functionality of the particularly this femoral head and acetabular socket. That is that they continuously wear out, and therefore patient has to go revision surgery, and one has to develop improved material combinations. The second one is the dental implants. So dental implants, again dental screws, whenever one has to go through this dental replacement. So this is the titanium based alloys which gets into the root of this dental root, and this titanium based alloys also they are often coated with some of the ceramic materials to improve their longevity as well. Now coming to this, when this material, when a biological cell comes in contact with the biomaterial surface, there are certain distinct events or biophysical events that take place. At the first stage, this is the hatched region, is the material surface. On the top of it, as you see, this is the proteins. Proteins that get absorbed. And these proteins at the next level, they interact with the cell surface receptors. And you know from your biology textbook that cell membrane has several cell surface receptors which essentially act like a tongue. So essentially they hold on to the proteins which are absorbed on the biomaterial surface. So from a basic understanding, scientific understanding, you know, the spherical object is never a stable configuration on an infinitely flat surface. So therefore, that spherical surface has to also change their shape and size, and that is how a biological cell also changes in shape and size, and that is possible because of the reorganization that has to take place inside the cytoplasm. So inside the cytoplasm, as you see, these string-like structures, they are essentially actin filaments or microtubules. These are the part of the cytoskeletal structures. And these cytoskeletal structures, when they reorganize, they allow the cell to expand on the biomaterial surface, and also they allow the cell to further grow on this biomaterial substrate. So this cytoskeleton, this combination of the cell surface receptors and the proteins, they form that focal adhesion complexes. So this more the number of focal adhesion complexes, more would be the firm attachment of the biological cell on a synthetic surface. Synthetic surface means these hatched region materials, they are not biological origin. They are essentially artificial materials which are produced in the laboratory and which you intend to implant in the biomaterial surface. Now the question I'm going to address is that can we instruct the cells to grow as per our wish? For example, if I want cells to grow in a circular manner, or is it possible I can instruct the cell to align in a particular straight line? How can we do that? Now, to answer these questions, we have done some certain study. For example, we have made certain materials which are of fibers form. As you see these fibers, and if you look at this micron bar, it is 200 nanometer. That means each of the fiber, they have a diameter of around 100 nanometer or 100 to 150 nanometer. Then we have used another advanced technique called photolithography. I'm not getting into more details of this technique, but what I wanted to show you, this photolithography essentially allows you to get a film or pattern film here. And then third one is a spin coating. Again, you get some carbon-based materials, they're precursors, and you make a film. Now you see that there are three different surfaces, but the material is the same, but their surface topography is different. Now, if we grow the cells on these three different materials, so this is the more details about that, what is the size and size distribution of the strips, circles and squares. that one can use using the photolithography technique. So you can see in all these cases, their topographical patterns or features are quite different. Now, if you grow the cells on this different surface topography, what you see here, that this is the case for the Schwann cells. Schwann cells and neuroblastoma cells, they are essentially cells of the nervous tissue in the nervous system. So essentially, these are the neural cells. And neural cells are very important because, as you know, that neurons, they essentially grow in a particular aligned manner. Now, what you see here, that when there is a square or rectangular kind of piece, the cells, what they do, they kind of align, and they also are able to bend along the edges where there is a transition of these rectangular features here. And in case of the carbon fibers, they essentially are growing along the fiber directions. So this is the way we can manipulate the way the cells, we can instruct the cells that how they should grow on a particular material surface. This is the images that we can obtain from fluorescence microscopy technique, and what fluorescence microscopy shows, you see that blue stained region, these are essentially nucleus of the cell, and you see the green stained region, these are essentially cytoplasm or cytoskeleton of the cells. So what we have learned from these very basic experiments, that if you have the rectangular strips on the material surface, then cells can grow either on the pattern or along the rectangular strips. So essentially, unidirectional growth can be realized. And if you have a rectangular, if you have a square patterns, then cells also can bend along the edges of the square pattern. In case of the circular pits, the cells have the unique ability to grow along the circumference of the circle as well. So the similar experiments also are conducted using neuroblastoma cells. As I mentioned a few minutes ago, that Schwann cells and neuroblastoma cells, there are two important type of cells of the neural system. And in this neuroblastoma cells also you can see that some of these neurofilaments extension that has taken place along the square pits and so on. Next question I'm going to throw before you, that is this: can we instruct biological cells to function by external field stimulation? What is the meaning of that? Now you have a cell population, and in this particular case I'll use the example of the stem cells. I mean, most of you have heard of the stem cells because it comes in the newspaper very often, very frequently. Can we instruct or can we change the functionality of the stem cells by giving electrical stimulation externally to the medium or to the culture medium where cells are being grown? So in order to answer this, I'll show you the results of some of the experiments, and I'm not again going into very details of the experiments, but I'll show you the relevance first. First of all, why electrical stimulation? As I've introduced in the beginning, that in a human body, there are several tissues are there, and out of that, these are the three electroactive tissues. One is the brain, second one is the skeletal muscle tissue, and third one is the heart or cardiovascular system. These tissues in these particular organs, they are essentially electrically excitable. So therefore, if these tissues are to be repaired or if these tissues are to be regenerated, we need to involve electrical stimulation at the region of the repair. So, what are the stem cells? So stem cells have the unique ability to transform into functionally specialized cells. So essentially, by definition, stem cells are non-specialized cell type, and they have three specific attributes, and these attributes are self-renewal, that means it can repair itself. Second one is a potency, that is the ability to differentiate, and third one is clonality, that is tendency to multiply themselves of same lineage. Now let me explain to you the very basic aspect of the stem cell biology. Now if you start with the stem cells, so either they can grow, they can proliferate, but without changing their functionality. Functionality means it will have a very specific function. Cells are able to where the cells can function themselves in a very specific manner. For example, if you have a mesenchymal stem cells like bone marrow derived stem cells, mesenchymal essentially means bone marrow derived stem cells, and it can go to adipocytes. Adipocytes means fat cells. It can go to chondrocytes. Chondrocytes means cartilage cells. Then it can also differentiate, like change its function to osteoblast. Osteo means bone. Osteoblast means bone forming cells. Then it can also undergo differentiation to muscle cells, and it can undergo differentiation to neurons. Now, so this is, if you understand this one, then we can follow the rest of the slides. So what are the different ways the cells can be stimulated? Like you can have different parallel plate flow or ultrasound stimulation. And in this particular case, I'll be showing you the power of the electric field stimulation technique. And how this electric field stimulation takes place. So suppose if you have two electrodes, and in a culture medium, this is just a schematic, just to show one single cell is adhering on a biomaterial substrate. Now, what are the factors from engineering perspective that are important, like how much electric field or how much volt you are applying. So electric field strength is nothing but volt divided by that distance between the two electrodes. Then how you are going to stimulate these cells. Then third one, what is the pulse duration? And fourth one, what is the nature of field application, like DC field versus AC field? Direct current versus alternating current. I mean, all these things you must have read in your basic physics. Now, in order to do these things, what we have used gold nanoparticles. Now, synthesis of the gold nanoparticles, it involves a lot of chemistry, and which you can follow very easily. This chemistry, I'll just show you that. So this is called citrate capped gold nanoparticle. So nanoparticle means their size must be less than 100 nanometer, right? So citrate capped means this yellow colored spherical particle is a gold nanoparticle, and on this certain capping agents is there. And what you see here, this is 50 nanometer, and these small particles, they are essentially 30 to 40 nanometer in size. So now these gold nanoparticles, what we are doing, we are trying to do some coating on this layer by layer based assembly. Basis gold nanoparticle and polyaniline is another polymer. So this is the different layers we are essentially forming. And what we do, this is a very nice experiment that we have done. We have grown the cells, human mesenchymal stem cells, that is bone marrow derived stem cells, in a gold nanoparticle loaded solution, with the expectation that gold nanoparticles, because of their extremely small size, they are being internalized. Internalized means they go and get into the cells, inside the cells. And we are growing the cells on the gold nanoparticle and polyaniline based coatings, and then we are applying the electric field from outside. So what it acts, this entire system acts like this internalized gold nanoparticle acts like intracellular actuator, and extracellular gold nanoparticles act like a extracellular actuator in the presence of the electric field stimulation. We have so this is about the more of this gold nanoparticle synthesis, citrate reduction technique. You have to tune the way the trisodium citrate has to be added, and then you have these polyl-lysine coated gold nanoparticles. Now, there are two types of field we have applied to the system. One is the DC field. DC means that frequency is 0, and AC means this is 100 milliseconds, 900 milliseconds, like that. So on to T off is essentially 1:9. So on time means 100 milliseconds the field is on. Off time means that is 900 milliseconds the field is off. Now there are two type of DC, but two type of field is being applied here to this particular system. And what you see here, very interesting result, that when you apply the DC electric field, then the human mesenchymal stem cells, they show more like neural-like cells. Why I'm saying neural-like cells? That cells, they elongate in one particular direction, much larger than the actual size of the cell. So this kind of morphology essentially suggests that mesenchymal stem cells undergo differentiation to neural-like cells. And what you see here, when we apply the AC electric field, like there is a T on versus T off, they also undergo morphological changes, but here these morphological changes, they are more suggestive of the cardiomyocytes or cardiac type of cells. So what is the thing that you have learned? That you can instruct the stem cells one time to change its functionality to neural cells. In other way, by applying the AC electric field, you can instruct the stem cells to undergo functionality change towards the cardiac cells. And this is what you can see here, that when you make this 1 Hz frequency, this typical tube-like morphology, that is very typical of the cardiac cells. Now, why 1 Hz frequency is important? Because the pulse rate of an adult, of a normal or healthy human being, is around 72 per second. So 1 Hz frequency essentially means it is essentially 60 per second, which is closer to that way the heart beats at a frequency of 1 Hz. So therefore, that promotes more like cardiac cells. You have learned in your school biology also about the cell cycle. Like a cell undergoes that G0, so G0 to G1 to S to G2 and particularly to M to mitosis phase. Now what happens during the differentiation process, we have seen that most of the cells, they are stuck at the G to M phase. That means cells are not able to proliferate. So what happens is that because of the electric field stimulation, cells are not able to grow or not able to proliferate, therefore differentiation process is enhanced. So this is how that is more clinical translation. So what we believe that these stem cells, if they are being stimulated by 1 Hz frequency, they can undergo differentiation to cardiac cells, and that would be very useful for cardiac clinical treatment as well. Now you have just last 10 minutes you have seen that how gold nanoparticles can be helpful in doing the stem cell based regenerative engineering. Now I'll show you that how ultra-small gold nanocrystals can kill bacteria. Now here we have used two different approaches that in this particular case we have used different chemistry, because here we are not using the term gold nanoparticles, we are using the term gold nanoclusters. And these gold nanoclusters, here we have used the chloroauric acid plus triphenyl phosphine. And using this particular wet chemical based synthesis approach, you get these gold nanoparticles, and the sizes of these gold nanoparticles, as you can see, it is even less than 10 nanometer. It's extremely fine nanoparticles. Now when we give these gold nanoparticles to some of the bacteria like prokaryotic cells like Staphylococcus aureus and so on, so there you can see the different molar concentrations of these bacteria. This particular bacteria is getting killed by the gold nanoparticles. Now what is the reason behind these gold nanoparticles antibacterial effect? It is essentially due to the reactive oxygen species and ROS generation. I'm not going into more details in that, but what I can show you, these gold nanoparticles, the gold nanoclusters are essentially very effective in killing not only bacteria, but also bacteria cannot grow further to form the biofilm formation. So this biofilm is one of the major aspects for the prosthetic infection in this particular case. Okay, now before I conclude, I'll show you only just brief of the example where I can show that how engineering approach, like for example, you might have heard in the newspaper quite a bit about the 3D printing, layer by layer manufacturing of the materials or additive manufacturing techniques. Now this particular quadrilateral, you can see this particular case, you can go from additive manufacturing to three-dimensional microstructure to preclinical to public health, like clinical trials. Public health essentially means when engineering is being translated to treat human beings. So these are the 2 or 3 examples that I'm going to show you before I stop. So first one is the 3D inkjet printing of biomaterials for healthcare applications. So here you can see this is the layer by layer fabrication techniques, and this is the powder particle based layer. On top of it, the binder jet drops the impacts, they get into the powder bed, they impregnate it, and then you form, after that post-heat treatment, then you form the 3D printed solids. Now what we have done in a recent clinical trials, now if a patient has a cranium defects here, so some part of that human brain is to, or some part of the human skull has to be replaced. And this, some part of the skull, when it is replaced, then we take a CT scan data of the human patients, then we process it, then according to these particular defects, we make a 3D printed structure which is fairly solid. Now this is the pre-operative case of the human patients, and you can see there is a large defect on the human cranium. Then we put this and then we do clinical trials. Of the post-operative, you can see that cranium symmetry is being restored. So this is one of the ways that we have shown that how 3D printing based manufacturing can be very beneficial to treat human patients. The second one is the ceramic femoral head for total hip joint replacement. I have shown you before that how ceramic femoral head is important for the total hip joint replacement. Here again, you can see how research is being conducted at the interface of engineering and biology. That is, you have a CAD model, and from the CAD model you can get the green component of this of the ceramic materials. In this particular case, it's a zirconia and alumina mixture of zircon and alumina. Then after that, you make these materials in the solid form by heating that material to around 1600 degrees Celsius, because it's ceramic, essentially the high temperature materials. Then we make this very nice femoral head, which is a very close dimensional tolerance. And then after that, we do a lot of biomechanical analysis just to show when it actually implanted in the human body, what is the stress level that it makes. And this is a typically 3D microstructure. Then we do all the cell level studies. This is the muscle cells which are being grown on this biomaterial substrate. Then after that, in vivo, that is the human trial in the animals, in the animal experiments. Then after that, our materials is ready to be seen. The second or third example that I'm showing is the dental implant. Now, many of you nowadays know from the class 9-10 that what is isometric projection, what is the 3D projections, how to make the different views of an engineering structure. For example, you want to make a dental implant. First thing you have to start with is what is the different parts of the dental implant system. Now, if you can do the virtual implantation in the computer and show that if the dental implant has this kind of thread, when you put it in the oral cavity, what is the stress level or what is the stresses that implants would be exposed, and whether this material would have that sufficient strength. And then you can do the biomechanical testing, like essentially you can simulate that oral maxial environment and mastication process, and to show that what is the stress level this material can experience, and then that can sustain. Then we have done, based on this analysis, we have done the indigenous implant, and then we have put it in the rabbit material. And also we can also compare that what is the commercial implant and how our implants they behave in terms of the microstructure and properties. So these are like few examples I thought, and this is the last example, that is the neobladder for bladder carcinoma. So many times human patients, they have a bladder cancer, and in case of the bladder cancer, the entire bladder has to be removed, but then where the urine is to be restored in those kind of patients. So you require artificial urinary bladder, and this bladder has to hold the urine of sufficient amount or sufficient volume, and for that we have got one project for last 1 year we are working on that. So how to make the artificial bladder? Then first is the polymer processing. So here we are using two different kind of polymers. When we mix it, we make a copolymer, and then copolymer, essentially we do a lot of testing, like whether this copolymer can have good encrustation or resistance against the salt deposition. That is one of the major important things. And after the incrustation resistance, then we do prototype, and then we do further implantation in that human patients. So with this, I would like to conclude my lecture by acknowledging different financial organizations for supporting our research. for last many years. Thank you very much.
Thank you very much, sir. So if you have any questions, so please ask him. If you have any questions.
Sir, you mentioned how we can differentiate stem cells into cardiac cells and neurons. Can we form other types of cells? Can we form other types of cells by changing the frequency of the AC field?
So what I've not shown that we have in elastically stiff materials like ceramic materials, when you have grown the human mesenchymal stem cells, with electric field stimulation we have shown that it goes to osteoblasts like bone cells. It is not using AC field but using the complete DC field we have done that. And you can essentially, in principle, you can even differentiate stem cells towards the cartilage cells, chondrocytes, all those things are possible.
Artificial bladder can be replaced in the patients. I think there should be lesser dangers to the patients in future. What do you think?
Yes, but the main challenge is to develop the polymeric materials which will have sufficient strain to hold the urine, and at the same time it should not encourage any salt deposition from urine. So if these two challenges are sorted out, then this artificial bladder that can be implanted into the human patients.
And the patient can live for long.
Yeah, I mean normally these bladder carcinoma patients, they are already 60, 65 average age of these patients. So at least these materials, if they are implanted, it can go for another 15, 20 years at least.
That's nice. Thank you.
Thank you.
Professor Rahul Banerjee, he will be our next speaker, and he will felicitate now Professor Bose. Please put your hands together.
Very good afternoon. বাংলায় বলবো না ইংরেজিতে? বাংলায় কক্সবাজার বললেই হলো and good জবরদস্তি নাকি? Okay, so everybody can hear me? Okay, very good. So very good afternoon. প্রথমেই ঠাকুর শ্রী মা আর স্বামীজিকে প্রণাম জানাই, and also very good afternoon to all of you. My name is Rahul Banerjee, and I am currently in ISR Kolkata, which is located in Mohanpur. Mohanpur na bole take dhadare Govindpur bolleo kom bola jay. So it is so far from here, and but it is a beautiful campus. Those who have not visited us, give an opportunity, take an opportunity to, and take a chance to visit us if you can. So in next half an hour, 45 minutes, I will try to describe, আমি চেষ্টা করব যে to discuss some of these burning problem or the burning questions. এই মুহূর্তে burning question কি in our mind? What is the burning question now? স্যার কখন শেষ হবে? এই লেকচার কখন শেষ হবে? That is the burning question. Okay, so that is right now the burning question. But if you look little bit beyond, then we should think ahead and think ahead of our time. There is আমি একটা ছবি দিয়ে শুরু করি তাহলে বুঝতে পারবে. So can anybody tell what is this picture? This is a plastic bag. This is a plastic bag which looks like iceberg, So it tells that what is the problem of today's situation. Problemটা কি? Problemটা হচ্ছে আমরা তো খেলাম, খাওয়া হয়ে গেল, জলের বোতল, তারপরে বোতল মাটি থেকে গঙ্গায়. This bottle is not completely, people say it is not biodegradable. It is not biodegradable. However, something can eat this bottle. You know what? Fish. They continuously eat it. And who eats fish? So you can imagine those things whatever যেগুলো তোমরা ভাবছো যে দেখলে সেগুলো ঘুরে তোমার কাছেই আবার ফেরত চলে আসে. And of course we can always say ওকে আমি হচ্ছে শাকাহারি, শুদ্ধ শাকাহারি, হ্যাঁ ঠিক আছে, দ্যাট ইজ ফাইন, কোনো অসুবিধা নেই। তাদের জন্য উই উইল কাম ব্যাক টু ইট লিটল বিট লেটার। তো যারা শুদ্ধ শাকাহারি, আমরা অনেকেই শুদ্ধ শাকাহারি, আমি তো। আচ্ছা, তো কামিং ব্যাক টু দ্য পয়েন্ট, সো এই পলিউশনের, এই যে বিভিন্ন রকমের পলিউশন, সেই নিয়ে যে বিভিন্ন রকমের পলিউশন, সেই নিয়ে যে এত ডিসকাশন চলছে, পলিউশনের রিয়েলিস্টিক্যালি সিচুয়েশনটা কি? লেটস থিংক লিটল বিট কেয়ারফুলি। পলিউশনের সংজ্ঞা, পলিউশনের ডেফিনেশন চেঞ্জেস উইথ টাইম। কে চেঞ্জ করে পলিউশনের সংজ্ঞা? চেঞ্জ করে হচ্ছে বিভিন্ন রকমের কোম্পানি। লেটস স্টার্ট উইথ দিস। এটা হেনরি ফোর্ড প্রথম এটা দেখিয়ে বলতেন যে এটা হচ্ছে ঘোড়ায় চলা গাড়ি, কোনো অসুবিধা নেই। তখন 1920 1930 সময় এটা হচ্ছে ঘোড়ায় চলা গাড়ি, এবং এইগুলো হচ্ছে যখন গাড়ি চলে সেগুলো ঘোড়া থেকে বেরোচ্ছে। তখন ফোর্ড বললেন যে দেখুন কি নোংরা, অ্যাবসলিউটলি ডিসগাস্টিং, ইউজ মাই কার, কমপ্লিটলি ক্লিন এয়ার, কোনো নোংরা নেই, কোনো আবর্জনা বেরোবে না, কিছু নেই, অ্যাবসলিউটলি পরিষ্কার পরিচ্ছন্ন জিনিস। এই হচ্ছে হেনরি ফোর্ডের ফোর সিলিন্ডার গাড়ির, তার পাশে দুটো গাছ হ্যাঁ লাগানো ইত্যাদি। এটা ছিল ফোর্ডের অ্যাডভার্টাইজমেন্ট। হেনরি ফোর্ড ফিয়েস্টা আমরা ইউজ করি অনেকে। আজকে আমরা খুব ভালো করেই জানি যে কোনটা মোর পলিউটিং দ্যান দ্য আদার, আমরা খুব ভালো করে জানি। তো এই হচ্ছে আজকের সিনারিও রিগার্ডিং দিস পলিউশনের প্রবলেমটা কি আছে? হোয়াট ইজ দ্য প্রবলেম অফ দ্য পলিউশন? উইল কাম ব্যাক টু দিস প্রবলেম ইন আ মিনিট। তো কারের যে সিচুয়েশন, এই যে কার থেকে যে এক্সস্ট বেরোচ্ছে, এক্সস্টে যে ধরনের পলিউটেড গ্যাস বেরোয়, সেই গ্যাস কি কন্টেন্ট করে? মেইনলি it contains carbon dioxide, it also contains sulfur dioxide, it also contains nitric, বিভিন্ন রকমের nitric, nitrous oxides. So sulfur dioxide যখন জলের সঙ্গে রিঅ্যাক্ট করে, it forms sulfurous acid, H2SO3, not SO4, SO3. That oxidizes later, becomes SO4, but sulfurous acid যদি আমাদের স্কিনের সঙ্গে আসে, it immediately starts penetrating through the skin. খুব মাইল্ড কনসেন্ট্রেশন বলে আমরা বুঝতে পারি না, কিন্তু মোর ইট উইল ইনক্রিজ, আমরা বুঝতে পারবো। প্রথম পয়েন্ট। সেকেন্ড, প্রত্যেক গরমের সময় মনে হয় আনবিয়ারেবল, আর পারা যাচ্ছে না, কি গরম। কেন? ওয়াই? বিকজ প্রত্যেকবার শুধু গ্লোবাল ওয়ার্মিং তো বটে, অফকোর্স গ্লোবাল ওয়ার্মিং। আমাদের ইন্ডিয়া হ্যাজ বিকাম মোর ওয়ার্ম দ্যান দ্য গ্লোব। ইন্ডিয়া একটু বেশি গরম হয়ে গেছে, তাই না? So this is the problem. So বিভিন্ন কিছু বছর আগে রতন টাটা একটা খুব সুন্দর লেখা লিখেছিলেন, আর বিভিন্ন নিউজ পেপারে বেরিয়েছিল। উনি বলেছিলেন যে আমার মৃত্যুর আগে আমি দেখতে চাই যে সমস্ত গাড়ি সারা পৃথিবীতে যেন সমস্ত গাড়ি জলে চলে, নট তেলে, ওয়াটার। এভরি কার ইন দ্য ওয়ার্ল্ড শুড রান ইন ওয়াটার। তো অবভিয়াসলি তোমরা অনেকেই হয়তো ভাবছো, স্যার সব বিকাল গুলমারার জায়গা পেলেন না, জল গাড়ি কখনো জলে চলে? That's absolutely correct. গাড়ি জলে চলতে পারে। আমরা যদি জলকে স্প্লিট করি হাইড্রোজেন এবং অক্সিজেনে using sunlight, and then take that hydrogen and oxygen and combine, we will again get water, but we will get something else, সেটা হচ্ছে energy, and that we can utilize to run not only the car but also everything else that we are running through the electricity. Believe me, যদি তোমরা ভবিষ্যতে কেউ রিসার্চ বা গবেষণা করতে চাও, দিস আর দ্য চ্যালেঞ্জেস ফর দ্য ফিউচার জেনারেশনের জন্য, যে টু সাম এক্সটেন্ট ইয়াঙ্গার কমিউনিটি শুড কাম ইনটু দ্য পিকচার আমার মতে। এবং তোমাদের মতন যারা ইয়াংস্টার্স, তাদের এই মাইন্ডসেট থাকা উচিত যে আই এম গোয়িং টু ওয়ার্ক অন দিস কাইন্ড অফ ফিল্ড and I will try to change the world by using my doing my work. So I'll come back to this point. So this hydrogen, সো আমি আবার করে আসি, জল থেকে স্প্লিট করলাম, পেলাম অক্সিজেন এবং হাইড্রোজেন, এবং সেই হাইড্রোজেনটাকে তারপরে আমাকে আবার কম্বাইন করতে হবে জল পাওয়ার জন্য। ওকে, অ্যাবসলিউটলি ফাইন। লেটস সে হাইড্রোজেন আমাদের বিভিন্ন রকম ভাবে আমরা জেনারেটও করতে পারি। দেয়ার আর মেনি ওয়েজ ইউ ক্যান জেনারেট হাইড্রোজেন। সো if we can generate hydrogen, let's say we will get the hydrogen from these sources. All right, আমাকে স্প্লিট করার দরকার নেই, we will save some time and money also. ঠিক আছে। So I will store hydrogen. Store hydrogen where? Store hydrogen in the car, right? I have to store it somewhere, right? I have to store the hydrogen. So এবার আমি আসল প্রবলেমে আসি, storing hydrogen. ওকে, কি প্রবলেম হচ্ছে এখান থেকে মোহনপুর রাফলি অ্যাবাউট 150 to 170 কিলোমিটার গিভ অ্যান্ড টেক আপ অ্যান্ড ডাউন। তো যাই আমি এখানে এসেছি, রাত্রিবেলা আমাকে বাড়ি ফিরে যেতে হবে অবভিয়াসলি। তো আমাকে যদি মোহনপুর থেকে এখানে এসে আবার বাড়ি ফিরে যেতে হয় সাপোজ 150 কিলোমিটার, তাহলে আমার লাগবে হচ্ছে 1 কেজি হাইড্রোজেন, 1 কিলোগ্রাম হাইড্রোজেন, 1 কিলোগ্রাম হাইড্রোজেন টু কাম ফ্রম মোহনপুর টু হিয়ার অ্যান্ড ব্যাক, বাড়ি ফিরে যেতে। 1 কেজি হাইড্রোজেন স্টোর করতে লাগে 1 মিটার বেলুন, 1 মিটার ডায়ামিটারের একটা বেলুন। গাড়ি পার্ক করার দরকার নেই, আমি কি গাড়ির পেছনে বেলুন লাগাবো? সো আই নিড টু কম্প্রেস and that's become the problem. কেন? কারণ হাইড্রোজেন হচ্ছে পিরিয়ডিক টেবিলের প্রথম এলিমেন্ট, the lightest element in the earth, lightest element. So obviously তো যখন আমি স্টোর করতে যাব, একটা সিম্পল উদাহরণ দিই। অনেকের বাড়িতে রান্নার গ্যাস আছে, কতদিন চলে? 1 মাস, মাস দেড়েক, ইভেন্টে 12 মাস নয় কেন? বা 12 বছর নয় কেন? 1 মাস কেন? Why 1 মাস? Anybody ever thought কেন? শেষ হয়ে যায়, অফকোর্স শেষ তো হয়ে যায়। কেন 1 মাসে শেষ হয়, কেন নয় 1 বছরে? কিভাবে আমরা রান্নার গ্যাসকে স্টোর করি? কি করে? লিকুইড ফর্মে। কিভাবে ব্যবহার করি? গ্যাস ফর্মে। তো লিকুইড থেকে গ্যাস, লিকুইড হিসেবে স্টোর করতে আমাদের গ্যাসকে লিকুইফাই করতে কি লাগে? প্রেসার, রাইট। তো গ্যাস যখন লিকুইফাই হয়ে প্রেসারের সিচুয়েশনে রয়েছে ইন রুম টেম্পারেচার, গ্যাস তখন কাউন্টার প্রেসার দেবে। গ্যাস কি ছেড়ে দেবে না? দে উইল গিভ কাউন্টার প্রেসার। সো সেই জন্যই সিলিন্ডারটা অতটা ভারী, সেটাই হচ্ছে ওটা থিকনেস। আমরা যদি কন্টিনিউয়াসলি প্রেসার দিয়ে লিকুইফাই করতে থাকি আরো বেশি পরিমাণে গ্যাস, সে কন্টিনিউয়াসলি এক্সট্রা প্রেসার দেবে এবং সিলিন্ডারের থিকনেস আমাদেরকে কন্টিনিউয়াসলি বাড়িয়ে যেতে হবে। সো ইভেন্চুয়ালি সেটা এত মোটা হয়ে যাবে সিলিন্ডারটা, উই উইল নেভার বি এবল টু লিফট ইট। দ্যাট ইজ দ্য প্রবলেম। প্লাস এর সঙ্গে সে গ্যাস পে বাই চান্স অ্যাক্সিডেন্ট হলে অনেক রকম প্রবলেম হতে পারে ইত্যাদি। সো দ্যাট ইজ দ্য প্রবলেম, দ্যাটস ওয়াই। সো উই আর স্টাক ইনটু আ লিটল বিট প্রবলেমেটিক রিজিয়ন, যে হাইড্রোজেন হচ্ছে লাইটেস্ট এলিমেন্ট ইন দ্য পিরিয়ডিক টেবল, তাকে লিকুইফাই করতে যে পরিমাণ হিউমাঙ্গাস এনার্জি লাগবে সেই এনার্জি আমাদের পক্ষে দেওয়া খুব মুশকিল। কিভাবে হাইড্রোজেন স্টোর করা হয়? বিভিন্ন রকমের সলিড অ্যাডসর্বেন্ট। তো আমি আগে কিভাবে হাইড্রোজেন স্টোর করা হয়? একটা তো হচ্ছে সিলিন্ডারে, যেটা আমরা ল্যাবরেটরিতে ব্যবহার করি, কিন্তু সেই যদি সিলিন্ডারে যদি হাইড্রোজেন গ্যাস হিসেবে স্টোর করা হয় কোনো অসুবিধা নেই। গাড়িতে আমি একটা সিলিন্ডার লাগালাম, গাড়ি স্টার্ট দিলাম, 2 হাত গেলাম, সিলিন্ডার শেষ, নতুন সিলিন্ডার। এরপরে আরো 2, তারপরে 4 হাত গেতে আবার 2টো সিলিন্ডার যায়। এরকম করে বাই দ্য টাইম আই রিচ টু দ্যাট ওভারব্রিজ, গোটা 25 সিলিন্ডার খতম। তো কে ঘাড়ে করে নিয়ে যাবে? তো সম্ভব নয়, দ্যাটস নট পসিবল। সো হাউ ডু উই স্টোর হাইড্রোজেন? Let's think a little bit. How can we store? We can store hydrogen in solid adsorbent, মানে solid adsorbent এ স্টোর করতে পারি। একটা ছোট ঘটনা বলি। রাত্রে এয়ারপোর্ট থেকে মোহনপুর মানে হরিঙ্গাটা ফিরছি, দেখছি বড় একটা ট্রাকে কয়লা ভর্তি, এবং সেই ট্রাকে কয়লা ভর্তি ট্রাকে ওপর থেকে জল দিয়ে কয়লার মধ্যে জল ঢালছে। আমি ড্রাইভারকে জিজ্ঞেস করলাম যে দাদা কয়লার মধ্যে জল ঢালছে কেন? আমি খালি অবাক হয়েছি, কয়লার মধ্যে জল ঢালছে কেন ভাই? কয়লা তো আর পরিষ্কার হবে না, কয়লা কালোই থাকবে, তাই তো? সাদা তো সে কোনোদিনই হবে না, বলে না? আমার ছোটবেলা বলতাম না তো কয়লার মধ্যে জল ঢালছে কেন? তারপরে ড্রাইভার আমাকে বললো, আমি আমার মাথায় আসেনি, কিন্তু বললো সিম্পল থিং, কয়লা কি করবে? জল ঢাললাম, জল ঢালার পরে কয়লা উইল অ্যাবজর্ব দ্য ওয়াটার ইনটু ইটস পোর, রাইট? কয়লা উইল অ্যাবজর্ব, লাইক ইট জলে চুবালে পরে যে ভারী হয়ে যায়, ঠিক সেরকম ভাবে কয়লা উইল অ্যাবজর্ব ওয়াটার। তারপরে লোকটা কি করবে? নিয়ে যাবে গাড়ির ট্রাক ভর্তি একটা লোকাল ওয়েইং মেশিনে, সেগুলোকে কাঁটা বলে। আমি জানি না তোমরা কেউ দেখেছো কিনা, বিরাট ওয়েইং মেশিন যেগুলো হাইড্রোলিক ওয়েইং ব্যবহার করা হয়, সেই কাঁটায় নিয়ে যাবে, একটা সার্টিফিকেট নেবে, 1 টনের কয়লা হয়ে গেছে এখন 1.5 টন। কে আর তুলে তুলে দেখছে কোন কয়লা শুকনো আর কোন কয়লা ভেজা? সার্টিফিকেট দেবে, সে 8 টনের বেশি টাকা নিয়ে বেরিয়ে চলে যাবে। That is called solid adsorbent. সেই কনসেপ্টে ব্যবহার করা হয়, where the water is nothing but hydrogen Our koala is nothing but new material. That's what the concept is, and that's what the target that you should always think of. New things, out of the box thinking college. আমার কিন্তু মাথায় আছে না, although I work in this field for quite some time. So this is the way you store hydrogen. There is another way you can store hydrogen. This is the way. So তোমরা কেউ কল্পনা চাওলার নাম শুনেছো? হ্যাঁ, okay. So the spacecraft in which she has gone, and this next generation spacecraft, a spacecraft gulo vertically they go up, and when they come back like a aeroplane. They don't come back, earlier days Sputnik এবং এগুলো যেগুলো আসতো সেরকম ভাবে নয়। কেউ গ্র্যাভিটি সিনেমাটা দেখেছে? Anybody? Yes. So when it comes down, as you can see, it comes down like exactly like straight, right? That's why there is so much heat generated আমাদের অ্যাটমসফিয়ারের মধ্যে দিয়ে যখন এটা পাস করে আসে। ঠিক সেরকম ভাবেই কিন্তু এই ধরনের স্পেসক্রাফট গুলো they come back like an aeroplane. So while coming down, there was some problem in the engine, and there was some combustion problem. So that's why the aircraft exploded. সেই নিয়ে তো আমি আর সেই ডিটেলে যাচ্ছি না। তো সেইখানে যে ফুয়েল ব্যবহার করা সেটা হচ্ছে লিকুইড হাইড্রোজেন ফুয়েল। সেই লিকুইড হাইড্রোজেনের সঙ্গে যখন সেটাকে আমি কম্বাস্ট করি, that gives so much pressure to the earth's crust. সেই প্রেসার ব্যবহার করে this whole thing along with the crew and all, সেই পুরো জিনিসটাকে তখন আমরা escape velocity achieve করতে পারি. So that goes up. So that is liquid hydrogen, the most expensive fuel in the earth. প্লেনের ভাড়া এত বেশি কেন? তার কারণ প্লেনে যে টারবাইন যে ইঞ্জিন ওটাকে ঘোরাতে যে পরিমাণ ফুয়েল লাগে, অত স্পিডে ঘোরাতে যে ফুয়েল লাগে, দ্যাট ফুয়েল হ্যাজ টু বি এক্সট্রিমলি পিওর। তাতে কোনো রকমের লোকাল কাটা কেরোসিন মিশিয়ে ওইসব চলবে না, তাহলে আপনি খানিক দূর গিয়ে তারপরে সেখানেই শেষ। তো কেরোসিন মিশিয়ে চলবে না, ইট হ্যাজ টু বি এক্সট্রিমলি পিওর। দ্যাটস ওয়াই টু পিউরিফাই সামথিং ইট কস্ট মানি, ভেরি সিম্পল। তো সেই জন্যই প্লেনের ফুয়েলের এত দাম বেশি, সেই জন্য প্লেনের টিকিটের দাম বেশি। খুব সিম্পল লজিক। তো সেটা ভাবে সেইভাবে আমি হাইড্রোজেন ব্যবহার করতে পারি। লিকুইড হাইড্রোজেন ভেরি এক্সপেন্সিভ, আনঅ্যাচিভেবল থিং। আমরা তাহলে আমাদের ব্যাগটা এখান থেকে মোহনপুর যেতে আসতে লাখখানেক টাকা লাগে, তো সেটা সম্ভব নয়। থার্ড ইজ দ্য সলিড অ্যাবজর্বেন্ট, সেই নিয়ে আমি আজকে বলতে চাইছি। তো বিভিন্ন ধরনের সলিড অ্যাবজর্বেন্ট আছে। সলিড কনসেপ্ট আবার বলছি, সেই জল, কয়লার মধ্যে জল অ্যাবজর্ব। অনেকের বাড়িতে অ্যাকোয়াগার্ড আছে নিশ্চয়ই। কেন্ট দেতা হয় সবচেয়ে শুদ্ধ পানি। তো কিভাবে কাজ করে অ্যাকোয়াগার্ড? So it comes, the water comes with all the contaminants. It passes through solid ceramic coating along with that same porous carbon. Porous carbon সেটাকে ফিল্টার করে ওই নোংরাগুলোকে, and you get clean water. খুব সিম্পল লজিক। সেইভাবে অ্যাকোয়াগার্ড কাজ করে। 6 মাস অন্তর অন্তর সার্ভিসিং করিও, আদারওয়াইজ ইট উইল বি আ ডিজাস্টার। ওকে, সো কামিং ব্যাক টু সলিড অ্যাবজর্বেন্ট, খুব ভালো কথা। তো সলিড অ্যাবজর্বেন্ট নিয়ে বিভিন্ন রকমের সলিড অ্যাবজর্বেন্ট, সেম যেরকম আমি বললাম, পোরাস কার্বন ইত্যাদি ইত্যাদি। তো সারা পৃথিবীতে অনেক লোকে বিভিন্ন রকমের সলিড অ্যাবজর্বেন্ট নিয়ে কাজ করছে, কার্বন ন্যানোটিউব, হাইড্রাইড ইত্যাদি ইত্যাদি। আমি আজকে একটা সলিড অ্যাবজর্বেন্ট নিয়ে বলবো, সেটাকে বলে মেটাল অর্গানিক ফ্রেমওয়ার্ক। আমি লিটল বিট, খুব বেশি নয়, খুব ডিটেলে যাওয়ার দরকার নেই। ওকে, সো যখন এই সলিড অ্যাবজর্বেন্ট নিয়ে রিসার্চ গবেষণা শুরু হয়, তখন ডিপার্টমেন্ট অফ এনার্জি, ইউনাইটেড স্টেটস অফ আমেরিকা, তারা একটা বেঞ্চ মার্ক দেয়। একটা আন্তর্জাতিক রিসার্চ করলেও ধরুন না, একটা তো টার্গেট থাকতে হবে না। তো টার্গেটটা কি আবার বলি, টার্গেটটা হচ্ছে এইটা। প্রথম টার্গেট হচ্ছে, টার্গেট খুব একটা হাই ফাই না। আমার যদি সলিড অ্যাবজর্বেন্ট 100 গ্রাম হয়, 100 গ্রাম সলিড অ্যাবজর্বেন্ট যদি আমার স্টোর করা থাকে সিলিন্ডারের মধ্যে, সেটা যেন 6 গ্রাম হাইড্রোজেন নিতে পারে। 100 গ্রাম সলিড অ্যাবজর্বেন্ট যেন 6 গ্রাম হাইড্রোজেন অ্যাবজর্ব করতে পারে, প্রথম পয়েন্ট। সেকেন্ড পয়েন্ট, প্রেসার 100 বারের যেন কম হয়। যত কম হয় তত ভালো। 1 বার হলে সবচেয়ে ভালো হয় অ্যাটমসফিয়ারিক প্রেসার, বা ঠিক আছে অ্যাটলিস্ট 100 বার তার যেন কম হয়। আজকে আমরা যে কমপ্রেস সিএনজি ভেহিকেল যে আমরা ব্যবহার করি, সিএনজি ভেহিকেলের প্রেসার, যে প্রেসারে যে গাড়িটাকে স্টোর করা হয় মিথেন গ্যাস, সেটা হচ্ছে 200 বার, 200 বার প্রেসার। ওকে, সো ডিওই টার্গেটটা 100 বার প্রেসার। মনে রাখবে, যত তুমি হাই প্রেসার দেবে ততই কস্ট বাড়বে এবং চান্সেস অফ অ্যাক্সিডেন্টসও বাড়বে। 100 বার। সেকেন্ড, থার্ড পয়েন্ট, সাইকেল। আমি হাইড্রোজেনটা স্টোর করব, রিলিজ করব, স্টোর করব, রিলিজ করব, স্টোর করব, রিলিজ করব, এরকম যেন অ্যাটলিস্ট 1000 সাইকেল হয়। থার্ড পয়েন্ট। ফোর্থ অ্যান্ড মোস্ট ইম্পর্টেন্ট পয়েন্ট ইজ টেম্পারেচার। কি টেম্পারেচার, যে এই মেটেরিয়ালটা যেন অ্যাক্টিভ থাকে বা পারফর্ম করতে পারে এক্স্যাক্টলি সেম ওয়েতে -30 ডিগ্রি থেকে +50 ডিগ্রি সেন্টিগ্রেড টেম্পারেচার, which means in this material should work in Alaska as well as in summer in Kolkata, everywhere. So আমি যদি বলি আমার গাড়ি শুধু আলাস্কাতেই চলে, এখানে চলে না, তাহলে তো চলবে না, আমার গাড়ি সব জায়গাতেই চলতে হবে, তাই তো? কে কিনবে নইলে? তো সেকেন্ড পয়েন্ট। So this is the most important point. So আমি আজকে যেটা নিয়ে বলতে চাইছি সেটা হচ্ছে এই মেটাল অর্গানিক ফ্রেমওয়ার্ক। সেই মেটেরিয়াল গুলো কিরকম ভাবে বানানো হয় সেটা নিয়ে বলি, কিভাবে লোকে ভাবলো এরকম ধরনের মেটেরিয়াল বানানোর জন্য। প্রথম পয়েন্ট হচ্ছে, যদি আমরা একটা জয়েন্ট নিই, একটা খুব সিম্পল লজিক দিয়ে একটা জয়েন্ট নেই, সেই জয়েন্টটাকে কানেক্ট করি আরেকটা জয়েন্টে এবং এটাই করতে থাকি, তাহলে আমরা একটা এরকম একটা স্ট্রাকচার বানাবো। অনেকটা একটা উদাহরণ দিলেই বোঝা যাবে, দুর্গাপূজার প্যান্ডেল, প্যান্ডেলের বাঁশটাকে যদি আমরা এই ধরি আর সেটাকে যখন যেটাকে বাঁধা হচ্ছে সেটাকে যদি আমি জয়েন্ট ধরি, সো খোলা বাঁশ দিয়ে কিছু করা যায় না, কিন্তু when we put them into a proper construction we construct a beautiful pandal out of it, যার মধ্যে দুর্গা প্রতিমা থাকতে পারে এবং দুর্গাপূজার সময় ওই দুর্গা প্রতিমা ওখানে রাখা আছে, কিন্তু দলে দলে লোক আমরা যাচ্ছি, কেউই দুর্গা প্রতিমা দেখছি না, অন্য কিছু দেখছি এবং ফটো তুলছি, সেলফি তুলছি, বেরিয়ে আসছি, সেটাই করছি, কিন্তু তাও এটা তো রাখা যায়। দ্যাটস দ্য কনসেপ্ট। সো আমার গেস্ট হচ্ছে হাইড্রোজেনটা হচ্ছে দুর্গা প্রতিমাটা এবং এই হচ্ছে তার জয়েন্ট স্ট্রাকচার। কিভাবে এটা কাজ করে দেখি, আমি একটা ছোট ভিডিও আছে, যদি সেটা চলে কিনা, লেটস ট্রাই ইট আউট। মেটেরিয়াল গুলো এগুলো হচ্ছে সলিড অ্যাবজর্বেন্ট, যেটা আমি বললাম। যদি আমরা এটাকে অনেক জুম করতে পারি, জুম আউট যেটাকে বলে জুম ইন, মানে অনেক বড় করে দেখতে পারি, it will exactly look like this. This is the porous material I am talking about. You can see the pores. I guess তোমরা সকলেই পোর্স গুলো দেখতে পাচ্ছ। যখন তুমি এক্সপোজ করবে তাকে হাইড্রোজেনের সামনে like this, it will start absorbing the hydrogen like a sponge, যেরকম স্পঞ্জ জল শুষে নেয়, ঠিক সেরকম ভাবে হাইড্রোজেন স্পঞ্জের মতো এটাকে শুষে নেবে এবং স্টোর করে রাখবে। দ্যাট ইজ দ্য কনসেপ্ট। কিভাবে স্পঞ্জের মতো শুষে নেবে, ঠিক এক্স্যাক্টলি দ্য ওয়ে স্পঞ্জ জল শুষে নেয়, ঠিক সেরকম ভাবে ইট ইজ জাস্ট বাই অ্যাবজর্পশন। অ্যাবজর্পশন প্রসেসের মাধ্যমে তোমরা নিশ্চয়ই অনেকেই পড়েছো কি করে গাছের মানে জল নিচ থেকে গাছের পাতা অবধি পৌঁছায়, সংশক্তি এবং আসঞ্জন, রাইট? ইয়েস, আই স্টিল রিমেম্বার। সো সেই সংশক্তি এবং আসঞ্জন, অ্যাডিশন এন্ড কোহেশন, এই ফোর্সের মাধ্যমে এটা ভেতরে ধরে রাখে। দ্যাট ইজ দ্য ওয়ে দিস হ্যাপেন্স। Okay, so I'll go back to the presentation now. Okay, and this is a real example. It is a real example. BASF, Ludwig Schafer, তোমরা যদি কেউ ইন্টারনেট রয়েছে একটু মোবাইলে বা কোথায়, তোমরা যদি চেক করতে পারো যে এই মেটাল অর্গানিক ফ্রেমওয়ার্ক সম্পর্কে। আমি আবার বলছি, মেটাল অর্গানিক ফ্রেমওয়ার্ক তৈরি হচ্ছে খুব সিম্পল জিনিস দিয়ে। এই যে টেরিপথ্যালিক বোতল রয়েছে, টেরিপথ্যালিক বোতল, এই যে পরে পিইটি বোতল বলে এটাকে, পলিইথিলিন টেরিপথ্যালেট। টেরিপথ্যালিক পলিমারের যে মনোমার সেটা হচ্ছে টেরিপথ্যালিক অ্যাসিড, যারা কেমিস্ট্রি নিয়ে পরবর্তীকালে পড়াশোনা করবে জানতে পারবে। টেরিপথ্যালিক অ্যাসিড, টেরিপথ্যালিক অ্যাসিডকে যদি তুমি জিঙ্ক নাইট্রেটের সঙ্গে বা যে কোনো মেটালের সঙ্গে রিঅ্যাক্ট করো, তুমি এই ধরনের প্রেসিপিটেট আর এরকম ধরনের সলিড বানাতে পারো। সেগুলো হচ্ছে প্রত্যেকটা বিউটিফুল এরকম পোরাস সলিড, এবং সেই পোরাস সলিড পাউডার সলিড গুলোকে যদি তুমি একটা সিলিন্ডারের মধ্যে ভর্তি করো, তাহলে 15 বার, এখানে অ্যারাউন্ড 20 বার প্রেসারে দেখানো হয়েছে। এটা হচ্ছে একটা এমটি খালি সিলিন্ডার, আর এটা হচ্ছে এই পাউডার দিয়ে ভর্তি সিলিন্ডার। নাও অবভিয়াসলি একটা কোশ্চেন জিজ্ঞেস মানে আমাদের মনে আসতে পারে, আমার সিলিন্ডারের মধ্যে তো পাউডার ভর্তি, তো গ্যাসটা কোথায় গেল, গ্যাসটা ঢুকবে কোথায়, তাই না? এটা অবভিয়াস একটা কোশ্চেন আসতে পারে। লেটস ট্রাই টু এক্সপ্লেন দ্যাট। এটা আমার এমটি সিলিন্ডার, খালি সিলিন্ডার। যদি এটা খালি সিলিন্ডার হয়, তাহলে যে গ্যাস মলিকিউলগুলোকে আমি ওর মধ্যে ভরবো, সেগুলো হচ্ছে সিলিন্ডারের গায়ের সঙ্গে, there is a Brownian motion, it will always try to anchor with something. এটা খুব সিম্পল লজিক। সিম্পল লজিক হচ্ছে এই, আমি সবাইকে বললাম বাইরে থেকে ভেতরে এসে বসো, আমরা কোথায় বসবো? চেয়ারে। কে আর মাটিতে বসবে এই বাজারে, রাইট? ঠিক সেরকম ভাবে এভরিবডি উইল অনলি অ্যাঙ্কার উইথ দ্য অ্যাঙ্কারিং পয়েন্ট। আমি যদি অ্যাঙ্কারিং পয়েন্টটাকে বাড়াতে পারি, লেটস সে এরকম ভাবে, আমি যদি এখানে সিলিন্ডারটাকে চেঞ্জ করে দিই, ধরা যাক আমি সিলিন্ডারের ভেতরে আমি ইলংগেটেড পয়েন্ট, কিছু সিলিন্ডারটাকে ইলংগেটেড পয়েন্ট ওখানে কি বলে আঠা দিয়ে আমি আটকালাম। ওকে, অলরাইট, দেন আই উইল গেট সাম মোর গ্যাস মলিকিউলস। আমি যদি সবকটা গ্যাস মলিকিউলকে বার করে আনি, আর ফ্ল্যাট একটা 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 করে সাজিয়ে রাখি এতে one by one, then I will get the number of gas molecules covered in a surface. Let us say this surface is 1 meter by 1 meter. Let us say this surface is 1 meter by 1 meter. So it is a called 1 meter square surface. প্রথম পয়েন্ট। ওকে, এবার আমি চেঞ্জ করতে পারি আমার সিচুয়েশন কিছুটা। লেটস সে আমি স্যান্ড বা বালি দিলাম, ওখানে বালির একটা এক্সট্রা সারফেস রয়েছে, বালি হচ্ছে ঠিক আছে, সেই বালি একটু এক্সট্রা অ্যামাউন্ট অফ গ্যাস মলিকুলকে অ্যাবজর্ব করতে পারবে only on the surface. All right, fine. So I will fill it up with sand, so it will absorb a little bit more. Let's say it will be 1 গ্রাম বালি আছে আমার কাছে, ওর মধ্যে ভর্তি, সেটা 10 by 10 মিটার স্কয়ার জায়গা দখল করতে পারে, সো 100 মিটার স্কয়ার। আর আমি যে মেটেরিয়ালগুলো এইমাত্র দেখালাম, যে মেটাল অর্গানিক ফ্রেমওয়ার্ক, সেটা শুধু আউটার সারফেসে নয়, সেটা ইনার সারফেসেও অ্যাবজর্ব করতে পারে, ঠিক এরকম ভাবে। So that becomes 100 by 100, which is 10,000 meter square per gram, and that's my target. Can you find out? Just try to find out what is the size of Salt Lake Stadium. Just find out how many meter square, and you can see how much unbelievable amount of space is there in these kind of materials that you can utilize for some purpose, and that's the purpose, to store hydrogen gas into this kind of materials. এটাই পারপাস, and এটাই টার্গেট, and এটাই হওয়া উচিত। দিস শুড বি আওয়ার টার্গেটেড ফিউচার। কি করে ডাইরেক্টলি মেজার করি, আমি অত ডিটেলে যাচ্ছি না, কি করে ডাইরেক্টলি মেজার করা যায় যে আমার কোন মেটেরিয়ালটা হাই সারফেস এরিয়া, কোনটা পোর সারফেস এরিয়া, কোনটা জিরো সারফেস এরিয়া। হাউ ডু আই মেজার? লেটস সে আমি আই পিক আপ সামওয়ান, আমি তোমাদের মধ্যে একজন কাউকে বললাম যে সবাই বেরিয়ে গেল, ঘরের মধ্যে কটা চেয়ার আছে, ঘরের মধ্যে না ঢুকে বল কটা চেয়ার আছে ঘরের মধ্যে। কি করে বলবে? হ্যাঁ, সবাই বেরিয়ে গেছে, তুমিও বেরিয়ে গেছো, কাউকে জিজ্ঞেস করবো, ওকে ভেরি গুড, কেউ নেই জিজ্ঞেস করার মতন, সবাই হিব্রু ল্যাঙ্গুয়েজে কথা বলছে, কেউ জিজ্ঞেস করার নেই, অথবা সংস্কৃত যেটা আমরা ভুলে গেছি। তো আমি বলি কিভাবে করা যাবে। আমি তোমাদের জায়গায় যেটা করতাম সেটা হচ্ছে বলতাম, একজন একজন করে বলতাম ভেতরে যাও, ভেতরে যাও। Okay, so galo, I will keep on counting, and at some point একজন এসে বেরিয়ে এসে বলবে, হ্যাঁ একটা চেয়ার ভেতরে খালি নেই, কোথায় বলবো আমি? Then I know how many chairs are there, because I counted, right? ঠিক সেরকম ভাবে I will dose gas molecules, I will dose gas molecules dose by dose, and I will keep on checking it, and at some point I will not be able to dose any further. Then I know this material can only contain this much gas. So এটা খুব সিম্পল লজিক, এইভাবে মেজার করা। তো এটাকে বলে সারফেস এরিয়া মেজারমেন্ট। বয়েলস ল ইউজ করে ব্যবহার করা হয়, P1 V1 equals to P2 V2। আমরা যেখানে প্রাইমারি প্রেসার জানি, প্রাইমারি ভলিউম জানি, সেকেন্ডারি প্রেসার চেঞ্জ আমরা মাপি, সেকেন্ডারি ভলিউম আমরা জানতে পারি, সেটা সিম্পল। সো দিস আর দ্য মেটেরিয়াল। সেই মেটেরিয়াল সম্পর্কে যেটা আমি বললাম, হাইড্রোজেন স্টোরেজ সম্পর্কে। তো এইভাবে হাইড্রোজেন স্টোরেজ আমি, so a MOF material, so metal organic framework, they can do যেটা আমি এইমাত্র দেখিয়েছিলাম, DOE target all these, প্রত্যেকটা করতে পারে এই MOF material extremely beautiful, except one, that is these materials are not active in room temperature. They can only perform at liquid nitrogen temperature, যেটা হচ্ছে 77 Kelvin। লিকুইড নাইট্রোজেনের ব্যবহার আমরা কি জানি, কিভাবে ব্যবহার করা? হ্যাঁ, ফ্রিজিং করতে, প্রিজার্ভ করার জন্য ব্যবহার করা, কারেক্ট, প্রিজার্ভ করার জন্য ব্যবহার করা। আর সিনেমাতে কেউ দেখেনি ধোঁয়া বেরোচ্ছে, কি করে আসে সেটা? লিকুইড নাইট্রোজেনের মধ্যে এক ফোঁটা জল দাও, হুড় করে ধোঁয়া বেরোচ্ছে, সেই ধোঁয়া তারপরে পেছনে পেছনে ছোট ছোট ভূতের আসছে, এই আসছে ওই আসছে, দ্যাট ইজ দ্য ধোঁয়া, সেটাই লিকুইড নাইট্রোজেন থেকে করা। তো এটা একটা ব্যবহার। তো লিকুইড নাইট্রোজেন টেম্পারেচার কেউ জানো টেম্পারেচার কত লিকুইড নাইট্রোজেনে? -77 কেলভিন। সো অবভিয়াসলি এবার যদি আমাকে বলে আমার গাড়ি -193 বা 195 ডিগ্রি সেন্টিগ্রেডে চালাতে, তো সম্ভব নয়, বাইরের টেম্পারেচার তো দেখেছি আমরা, তাই তো? হ্যাঁ, বেরোলে পরে একদম বেগুন ভাজা হয়ে যাবে, তো সেটা সম্ভব নয়। So if that is the case, then I have to figure out a way how to make I have to figure out a way how to make a material যেটা কিনা রুম টেম্পারেচারে কাজ করবে সেটাই হচ্ছে টার্গেট, এন্ড দ্যাট ইজ দ্য সায়েন্স। কি করে করবো আমি? সো আমি কিভাবে চিন্তা ভাবনা করে কিভাবে করবো, একটা দুটো উদাহরণ দেই তাহলে একটু আইডিয়া করা যাবে। উদাহরণটা হচ্ছে খুব সিম্পল থিং। আমি যদি এই মেটেরিয়ালগুলো ইনার কোরে, আমার সমস্যা এখন হচ্ছে these materials are binding with hydrogen but not that strongly. তো আমাকে এই মেটেরিয়ালের ইনার কোরটাকে চেঞ্জ করতে হবে। চেঞ্জ করলে দিস মেটেরিয়াল উইল বাইন্ড উইথ হাইড্রোজেন স্ট্রংলি। আমি আরেকটা উদাহরণ দেবো কার্বন ডাইঅক্সাইডের রেসপেক্টে, তাহলে বুঝতে পারবে, বাট আমি হাইড্রোজেনে আর ডিটেলে যাচ্ছি না। সো আই উইল নেক্সট 15 minutes I will discuss little bit about carbon dioxide. So recently টাটা স্টিলের সঙ্গে আমরা একটা প্রজেক্ট করছি, সেই প্রজেক্টটা আমি ডিটেলে বললে বুঝতে পারবে। টাটা স্টিলের ব্লাস্ট ফার্নেসে যে এয়ার পুশ করা হয় সেটা হচ্ছে রেগুলার এয়ার, হচ্ছে দে এক্সট্রাক্ট এয়ার and they push it to the blast furnace to keep it cold, blast furnace temperature. আচ্ছা, তো এই এয়ারটা যখন ওরা পাস করে, this air has to be moisture free, কোনো ময়সা থাকলে চলবে না এয়ারে। ওকে, তো এয়ারকে আমি ময়সচার ফ্রি করবো কি করে? অ্যানাইড্রাস ওকে, অ্যানাইড্রাস ক্যালসিয়াম ক্লোরাইড, ক্যালসিয়াম ক্লোরাইডের মধ্যে দিয়ে পাস করলে কি পাবো আমি? হ্যাঁ, কি হবে? ময়সচার ফ্রি তো বুঝলাম, কিন্তু হবেটা কি? হ্যাঁ, কি হবে তারপর? ওয়াটার তো অ্যাবজর্ব করলো, কি হবে তারপরে? ক্যালসিয়াম হাইড্রোক্সাইড, দ্যাটস কারেক্ট, ক্যালসিয়াম। তো ওরা যেটা করে, ক্যালসিয়াম ক্লোরাইডটা পাবো কোথা থেকে? ক্যালসিয়াম ক্লোরাইডটা কোথা থেকে পাবো? হ্যাঁ, মাইন করতে হবে, কারেক্ট। ওকে, তো মাইন করতে খরচা কে দেবে? প্রিসাইসলি না গভর্নমেন্ট নয়, না টাটাও নয়, ইয়েস আমরা দেবো, ওরা দেবে না, ওরা কেন ফ্রি দেবে? কারেক্ট। নাও সেই জন্য what they figured out যে ক্যালসিয়াম ক্লোরাইড ইজ বিট এক্সপেন্সিভ, তো তার কাউন্টার আমাদের কাছে কাউন্টার মেটেরিয়াল কি থাকতে পারে? it will be viewed more expensive. আর ক্যালসিয়াম রিলেটেড আর কি? ক্যালসিয়াম অক্সাইড, কারেক্ট, ক্যালসিয়াম অক্সাইড, দ্যাটস কারেক্ট। কিন্তু ক্যালসিয়াম সিলিকা জেল is also silica, right? After all, we have to understand সিলিকা ইজ বালি। দেখতে মানে যে বললেন এটা, আজকে বাড়ি বানাতে, এক একটা বাড়ি বানাতে কত টাকা করে খরচা হয়, ফ্ল্যাটের দাম আকাশ ছোঁয়া, তাই না? So silica is not a very high alternative. So calcium, coming back to the calcium, কি করে ক্যালসিয়াম অক্সাইড আসবে? From calcium carbonate, right? Okay, so calcium carbonate to calcium oxide আমি যখন হিট করব, প্রিসাইসলি কি হবে? ক্যালসিয়াম কার্বনেটটা যখন হিট করব, এক্স্যাক্টলি, নাও ইউ ক্যান সি কোথা থেকে CO2 আসছে। সো CO2 বেরোবে পার ডে 2.5 মেট্রিক টন পার আওয়ার CO2 বেরোয় টাটা স্টিলের ফার্নেস থেকে। বিকজ অফ দিস they need the calcium oxide. যদি আমরা ইউজ করি P2O5, সিলিকা জেল, এক্সেট্রা অল দিস থিংস, তাহলে যেটা হবে, ওই যে স্টিলের থালা বেরিয়ে আসবে, তাহলে ওই সারা জীবন ওই একটা করেই স্টিলের থালা হবে আমাদের। That will be that expensive, right? So ওই কার্বন ডাইঅক্সাইডটা কি করা যাবে? অ্যাটমসফিয়ারে গেল, দিনের পর দিন, বছরের পর বছর, যদি কালকে আমরা বলি গ্লোবাল ওয়ার্মিং, তাহলে কি লোকে ছেড়ে দেবে? ওকে, ড্রাই আইস, কিন্তু কতটাই বা ইউজ ড্রাই আইস, কতটাই বা ইউজ, ওটা ইউজ করতে হবে। তো ওটাকে কি করি আমরা? গাছে একটা জিনিস মাথায় রাখতে হবে, গাছেরও কার্বন ডাইঅক্সাইড অ্যাবজর্ব করার একটা ক্ষমতা আছে। হ্যাঁ, ওকে, 2.5 metric ton per hour, সারা বাড়িতেই গাছ লাগাতে, যেটা করা হয়, তাই দিয়ে টাটা স্টিল ওরা বিক্রি করে কার্বন ডাইঅক্সাইড। কোথায়? বেভারেজ ইন্ডাস্ট্রি, স্প্রাইট, সেইখানে বিক্রি করে। That is called bottling the carbon dioxide. Okay, বিক্রি করে। That's what it is. That's what the coke, that's what the carbon dioxide you are drinking every day. every single time. Remember that. So ওরা বিক্রি করে ওটাকে, এটাকে বলে অনুসারী শিল্প। ওকে, সো এবার যদি পয়েন্টে আসে, সো এই কার্বন ডাইঅক্সাইড যেটা বিক্রি করছে, রিমেম্বার রতন টাটা প্যারিসে গিয়ে এগ্রিমেন্ট সাইন করে এসেছেন in 2020. The Tata Steel needs to cut down this emission to 1.7 cubic ton. Right now they are doing 2.3. So ওরা বিভিন্ন রকমের চেষ্টা করে দেখেছে যে whatever they are emitting right now, out of which around 0.6 cubic ton, যেটা হচ্ছে 2.3 minus 6 is 1.7, সেটাকে ওরা বটলিং করতে পারে। But in order to make it profit, what they want to do is they want to bottle more to sell it to other places, right? So কিভাবে আমি অ্যাবজর্ব করব কার্বন ডাইঅক্সাইড? I will once again same কয়লার concept. I will fill my সিলিন্ডারের মধ্যে সলিড অ্যাবজর্বেন্ট দেবো, কার্বন ডাইঅক্সাইড অ্যাবজর্ব করাবো, কার্বন ডাইঅক্সাইড ওর মধ্যে অ্যাবজর্ব করবে, লট অফ কার্বন ডাইঅক্সাইড হবে, অ্যাবজর্ব করানো যাবে, আমার ট্রান্সপোর্টেশন কস্ট হবে মিনিমাল, এবং I will have a more profit. This number goes in crores, tens of crores actually. This goes, so সামান্য একটু এদিক ওদিক, it can cut down your profit to tens of crores. এই লেভেলে চিন্তা করছি। সো কিন্তু প্রশ্নটা হচ্ছে যে এই ধরনের কার্বন ডাইঅক্সাইড যদি আমরা কন্টিনিউয়াসলি ব্রেভারেজ ইন্ডাস্ট্রিকে বিক্রি করতে থাকি, ব্রেভারেজ ইন্ডাস্ট্রি কতটা কিনবে? কারণ সেই ব্রেভারেজটা কাউকে খেতে হবে ইভেনচুয়ালি। তো আমরা যদি ওই 1.7 এর নিচে আসতে চাই, তাহলে দিন রাত্রির আমাদেরকে শুধু কোকা কোলাই খেয়ে যেতে হবে, সেটা সম্ভব নয়। সো হোয়াট উই আর সাপোজ টু ডু দেন, হোয়াট শুড উই ডু? আরেকটা জায়গায় কার্বন ডাইঅক্সাইড বেরোয়, সেটা হচ্ছে আমাদের থার্মাল পাওয়ার প্ল্যান্ট, টিটাগড়, কোলাঘাট, সাঁওতালডি, ব্যান্ডেল ইত্যাদি ইত্যাদি। কিন্তু সেখানে সেই কার্বন ডাইঅক্সাইডটা ট্রিটমেন্ট করা হয়, যে ট্রিটমেন্ট হয় সেই ট্রিটমেন্টকে বলে অ্যামিন ট্রিটমেন্ট। তোমরা যখন পরবর্তীকালে পড়বে, কার্বন ডাইঅক্সাইড এর সঙ্গে জলের রিঅ্যাকশন হলে কি হয়? কার্বনিক অ্যাসিড। তো কার্বন ডাইঅক্সাইড ইজ অ্যাসিডিক, অ্যামিন ইজ বেসিক। তো অ্যাসিড প্লাস বেস সল্ট। ঠিক সেরকম ভাবে অ্যামিনের সঙ্গে যখন কার্বন ডাইঅক্সাইড রিঅ্যাকশন হয়, একটা সল্ট প্রেসিপিটেট করে, যেটাকে বলে কার্বামেট সল্ট। তুমি সেই সাদা সল্টটা পিক আপ করতে পারো, হিট ইট আপ, ইউ গেট দ্য অ্যামিন, ইউ রিজেনারেট দ্য অ্যামিন এন্ড ইউ গেট দ্য কার্বন ডাইঅক্সাইড। ইউ ইউজ দ্য কার্বন ডাইঅক্সাইড ফর দ্য সেম পারপাস। এই প্রসেসটা এক্সিস্ট করে রেগুলার অল ইন্ডাস্ট্রিতে এই মুহূর্তে। বাট ওয়ান্স अगेन, হু পেজ ফর ইট? 40 পয়সা প্রতি টাকা যে ইলেকট্রিসিটি বিল হয়, তার 40 পয়সা যায় হচ্ছে এই টেকনোলজি। ইয়েট দিস টেকনোলজি ইজ নট ভেরি স্ট্রং হোল্ড টেকনোলজি। তো ঠিক সেরকম পয়েন্টে সেজন্য আমাদেরকে টাটা স্টিল বললো যে আপনারা যদি এখন কিছু করতে পারেন যাতে করে আমরা এই কার্বন ডাইঅক্সাইডটাকে স্টোর করতে পারি একটা কন্টেনারের মধ্যে ইন এ লার্জ কোয়ান্টিটি, সো উই ক্যান স্টোর দেম এন্ড স্ট্যাক দেম আপ in a extremely, and then we figure out what to do. কার্বন ডাইঅক্সাইড থেকে আমরা আর কি করতে পারি? উই ক্যান মেক পলিকার্বনেট। পলিকার্বনেট কোথায় ব্যবহার করা হয়? গাড়ির কাঁচে। সেজন্যই গাড়ির কাঁচে যদি কেউ ঢিল মারে, কাঁচ টুকরো হয়ে যায় না, চিড় ধরে, কারেক্ট? একটা শ্যাটারিং হয়, তাই তো? বিকজ ইটস এ গ্লাস এন্ড পলিকার্বনেট মিক্সচার। সো গাড়ির কাঁচে, বিভিন্ন রকমের জানলার কাঁচে ইত্যাদি জায়গায় ব্যবহার করা হয়। তো সেই কার্বন ডাইঅক্সাইডের ব্যবহারের জন্য so we are now making these different type of porous material, যেগুলো কিনা এই সিলিন্ডারের মধ্যে ওরা ভর্তি করবে, and then it will contain almost 13 to 20 times of our empty cylinder. সেটা এখন টার্গেট। কিভাবে? একটা উদাহরণ দিয়ে দেখাই। এরকম আমরা একটা মেটাল অর্গানিক ফ্রেমওয়ার্ক ব্যবহার করছি, যেখানে একটা এরকম অ্যামিন রয়েছে, এবং এই অ্যামিনটা দিয়ে যখন এই মেটেরিয়ালটা বানাই, এই সলিডটা, আমি একটা উদাহরণ দিলে দেখতে পাবো, এই হচ্ছে কার্বন ডাইঅক্সাইড। as you can see, এটা একটা রিয়েল ক্রিস্টাল স্ট্রাকচার, এবং দেখতে পাচ্ছ তুমি কার্বন ডাইঅক্সাইড কিরকম ভেতরে পোরের মধ্যে অ্যাবজর্ব হয়ে আছে। ঠিক এরকম ভাবে আমরা কার্বন ডাইঅক্সাইড অ্যাবজর্পশন করি এবং কার্বন ডাইঅক্সাইড দিয়ে একটা মেটেরিয়ালের মধ্যে স্টোর করে রাখতে পারি। তো এটাই আমাদের টার্গেট, এটাই হচ্ছে CO2। আমি যেটা আজকে বলতে চাইছিলাম, হাইড্রোজেন স্টোরেজ এবং CO2 ক্যাপচারের উপরে আই বিলিভ যে তোমরা বুঝতে পেরেছো, তোমাদের একটা আইডিয়া হয়েছে যে কিভাবে এই মেটেরিয়াল গুলো ব্যবহার করা যায় আর কিভাবে মেটেরিয়াল গুলো নিয়ে কাজ করা যায়। আমরা এর উপর ফার্দার কিছু কাজ করেছি, সেটাকে বলে পলিমারিক 2 ডাইমেনশনাল পলিমার নিয়ে, কিন্তু আজকে সময় অভাব, সেই জন্য আমি আরো তো ডিটেলে যাচ্ছি না ওটার ব্যাপারে। এবং আই বিলিভ যে এই ধরনের মেটেরিয়াল উপর তোমরা কাজ করতে পারবে, এই ধরনের মেটেরিয়াল উপর তোমরা রিসার্চ করতে পারবে। এবং obviously this research is not very easy, আমি 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 এই নিয়ে কোনো রকমই ইয়ে নয় বা দ্বিমত নেই আমার, এবং সেই জন্য তার চ্যালেঞ্জ হাইয়ার, তার রিওয়ার্ড উইল বি হাইয়ার। আমি একটা ছোট রবীন্দ্রনাথ ঠাকুরের একটা ছোট উক্তি দিয়ে শেষ করি। রবীন্দ্রনাথ ঠাকুরকে এসে একজন বলেছিলেন, কি কঠিন কঠিন কবিতা লেখেন, কিছু বোঝা যায় না, হ্যাঁ, আপনি সোজা করে লিখতে পারেন না? তখন রবীন্দ্রনাথ ঠাকুর বলেছিলেন, সহজ করে কইতে আমায় কহজে, সহজ কথা যায় না বলা সহজে। থ্যাংক ইউ ভেরি মাচ ফর ইউর অ্যাটেনশন।
ওদের যদি কিছু কোশ্চেন করার থাকে জিজ্ঞাসা করবো তাকে। উনি খুব ভালো মাস্টারমশাই, এটা বোঝা গেল, কারণ এরকম আছে যে হ্যাঁ, yes, please come on.
Sir, you have told that we can store hydrogen or carbon dioxide in metabolism framework, but when we want to use it,
yes,
again, so how can we remove from it?
Just release the bulb.
Just release the bulb.
Exactly, it is a physical absorption.
Okay.
Just release the bulb.
So some amount of gas will be there.
There will be a dead bulb, but it is very small amount. So we have to leave it. But just release the bulb. আর কেউ কিছু প্রশ্ন করবে? দেখো, উনি সূর্য যত পশ্চিম দিকে ঢলে যায় তখন আমাদের ইন্টারেস্টটাও কমে আসে। উনি কিন্তু খুব চালাকি করে তোমাদের ইন্টারঅ্যাকশন, একটা সেশন নিয়ে, ইন্টারঅ্যাক্টিভ সেশন নিয়ে সুন্দর তোমাদের মাতিয়ে রাখলেন, বুঝিয়ে দিলেন। খুব ভালো, গুড পলিসি। আগের সবাই দেখেছে ওরা একাই বলে যাচ্ছিলেন, ইনি দেখলেন আমি শেষ বেলায় এসেছি, সবাই বোর এমনিতেই, তো তোমাদেরকে বেশ জাগিয়ে রেখে ভালো বললেন, এটা ভালো লেগেছে। তাই জন্য বললাম খুব ভালো মাস্টারমশাই। কারো কিছু যদি বলার থাকে জিজ্ঞাসা করো। সবাই বুঝে গেছে। এবারে মহারাজ আপনি সব ফেলিসিটেট করবেন। মহারাজ আমরা কৃতজ্ঞ।
বেশি সময় নেব না, আমি জানি তোমাদের বাড়ি যাওয়ার তাড়া, অনেক দূর থেকে এসছে, খুব ভালো লাগছে। তোমরা যারা এখানে তো লোকাল, যারা নরেন্দ্রপুর স্কুলে যারা আছো, শুধু মেদিনীপুর থেকে অনেক স্টুডেন্টরা এসছে এখানে, অনেক ছাত্রছাত্রীরা এসছে, খুব ভালো লাগছে। এবং তোমরা পুরো সারাদিন এই প্রোগ্রামটাকে এনজয় করেছো, এটা খুব ভালো। আমি আর তোমাদের মধ্যে আর তোমাদের ক্লান্তিটাকে আর দীর্ঘায়িত করবো না, আমি খুব তাড়াতাড়ি সংক্ষেপে এটাকে শেষ করার চেষ্টা করব। এবং আমি সত্যি এত সুন্দর এই প্রোগ্রাম অ্যারেঞ্জ করার জন্য আমি প্রথমেই এই টকের শুরুতেই আমি এই নরেন্দ্রপুর রামকৃষ্ণ মিশন বিদ্যালয়ের কর্তৃপক্ষকে, হেড মহারাজকে আমি অসংখ্য ধন্যবাদ জানাই। এবং যারা ভলেন্টিয়ার আছে এখানে, খুব সারাদিন খুব কাজ, খুব পরিশ্রম করে এই প্রোগ্রামটাকে সাকসেস করেছে, তাদেরকে ধন্যবাদ জানাই। নাও আমি এখন টকে ফিরে যাচ্ছি। তোমাদের বাড়িতে যে ডিসপ্লে ইউজ করো, বেশিরভাগ তোমাদের বাড়িতে, একটু হাত তুলে বলতে পারো কারা কারা এলসিডি ডিসপ্লে বাড়িতে দেখেছো, বা কারা কারা এলইডি ডিসপ্লে দেখেছো? এলসিডি কারা কারা দেখেছো? এলসিডি ডিসপ্লে, আচ্ছা। এলইডি ডিসপ্লে বাড়িতে কারা কারা দেখেছো? আচ্ছা। ও কোয়ান্টাম ডট ডিসপ্লে, কিউএলইডি কতজন দেখেছো? আজকে ইউজ করেছো? আমি তাহলে একটা অন্যরকম ডিসপ্লেতে যাই, যেটা এলসিডি নয়, এলইডি নয়, কোয়ান্টাম ডট ডিসপ্লেও নয়। এবং এইটা জানতে গেলে আমাদের জানতে হবে যে ইলেকট্রন কত রকম ভাবে এমিট হতে পারে একটা মেটেরিয়াল থেকে। Actually, it may be three kinds. One is harmonic emission, where electron emits by application of thermal energy. Second one is photoelectron emission, where electron emits by application of photon. And last one is the field electron emission, where electron emits by application of electric field. And the field electron emission is nothing but the discharge of electron from a surface of a material by application of electric field. এবং এই ফেনোমেনাটাকে ব্যবহার করে এক নতুন ধরনের ডিসপ্লে বানানো হচ্ছে, সেটার নাম হচ্ছে ফিল্ড এমিশন ডিসপ্লে বা কোল ক্যাথোড ডিসপ্লে। এবার আমি ধীরে ধীরে যাব যে আমি এতক্ষণ ধরে আমি যে ডিসপ্লেগুলোর নাম শুনেছি, এলসিডি, এলইডি, কোয়ান্টাম ডট ডিসপ্লে, এর বাইরে এই যে ফিল্ড এমিশন ডিসপ্লে, এর আবার কি তাৎপর্য, সিগনিফিকেন্স আছে বা এর কি কি অ্যাডভান্টেজ আছে। এই field emission display consists of actually cathode and anode. When voltage is applied between the cathode and anode, the electrons are ejected out from the cathode tip and it strikes on the anode surface. The electronic transition takes place and we get light at the top of the surface. Actually, এর অ্যাডভান্টেজ গুলো কি? আমি এখন যে প্রিভিয়াস ডিসপ্লে গুলো বললাম, বলছে ক্যাথোড রে টিউব বা ক্যাথোড রে মনিটর যেগুলো বাড়িতে আমরা ইউজ করতাম, তার থেকে এর রেসপন্স টাইম খুব ফাস্ট। মানে আমি সুইচ দেওয়ার সঙ্গে সঙ্গে কিন্তু আমি অন করতে পারি মনিটর। সেকেন্ড, যেটা মেন অ্যাডভান্টেজ, যে একটা এলসিডি স্ক্রিনে, মানে আমি একটা 19 ইঞ্চ যদি একটা স্ক্রিন ইউজ করি, তাতে কারেন্ট কনজাম্পশন বা পাওয়ার কনজাম্পশন নরমালি 30 ওয়াট, নরমালি তোমরা লক্ষ্য করে থাকবে। কিন্তু যদি আমি ফিল্ড এমিশন ডিসপ্লে ইউজ করি, তার পাওয়ার কনজাম্পশন অনলি 12 ওয়াট, মানে প্রায় হাফ অফ এন এলসিডি সিস্টেম। এবং লাস্ট যেটা আরেকটা ইম্পর্টেন্ট অ্যাডভান্টেজ আছে, যেটা ব্যাকলাইট লাগে না। তো রিসেন্টলি লাস্ট 2 বছর আগে সোনি ডেভেলপ করেছে এই ফিল্ড এমিশন ডিসপ্লে ইউজিং কার্বন ন্যানোটিউব। এবং এই কার্বন ন্যানোটিউব ওরা ক্যাথোড মেটেরিয়াল হিসেবে ইউজ করেছে। অলরেডি আমি বলেছি যে ফিল্ড এমিশন ডিসপ্লে দুটো পার্ট, একটা হচ্ছে ক্যাথোড পার্ট, একটা অ্যানোড পার্ট। এই ক্যাথোড পার্টটাতে মেন যে মেটেরিয়ালটা লাগে সেটা হচ্ছে কার্বন ন্যানোটিউব, এবং খুব কস্টলি। প্রায় 1 গ্রাম কার্বন ন্যানোটিউবের জন্য কস্ট হচ্ছে 5000 রুপিস। এছাড়া মানে ভেরিয়াস মেটেরিয়ালস আর ডিফারেন্ট ফিল্মেটিং মেটেরিয়ালস আর অ্যাভেলেবল ইন লিটারেচার। ওয়ান ডাইমেনশনাল মেটেরিয়ালস আর ওই কার্বন ন্যানোটিউব, and inorganic nanostructures are zinc oxide SNO2, and organic nanostructures are organometallic material like copper phthalocyanine, aluminum quinone. আমরা এই কার্বন ন্যানোটিউবের বাদ দিয়ে, যেহেতু আমরা অলরেডি আমি বলেছি এর কস্ট খুব হাই, আমরা নতুন এক ধরনের ন্যানোটিউব বানানোর চেষ্টা করেছি। এবং এই ন্যানোটিউবটা হচ্ছে অর্গানোমেটালিক ন্যানোটিউব। আমরা একটা সুন্দর মেথড অ্যাপ্লাই করেছি, একটা প্রসেস অ্যাপ্লাই করেছি, যেই প্রসেসে আমরা মার্কেট থেকে কমার্শিয়ালি এই অর্গানোমেটালিক বা কপার ফ্যালোসাইনিন পাউডার কিনে আমরা বিভিন্ন, আমি আলোচনা করব না এখানে, বিভিন্ন ট্রিটমেন্টের মাধ্যমে আমরা এই কপার ফ্যালোসাইনিন একটা অর্গানিক ন্যানোটিউব বানিয়েছি আমরা। এবং শুধু মেটেরিয়ালটা তো বানালে হবে না, কোন একটা মেটেরিয়াল বানালাম সেটা ঠিক না ভুল কি করে টেস্ট করব বলতে পারবে? ফার্স্ট কিভাবে চেক করো? কোন একটা কম্পাউন্ড বানালাম, কোন আইডিয়া? আচ্ছা, কে কে নাম শুনেছো? জিঙ্ক অক্সাইড নাম শুনেছো? টাইটানিয়াম অক্সাইড নাম শুনেছো? আচ্ছা, টাইটানিয়াম অক্সাইড পিওর না ইমপিওর কি করে বলবো? কেউ তোমাকে যে কোনো একটা সাপ্লায়ার দিয়ে যায়, কি করে বলবে? কোনো আইডিয়া নেই না? তো বলতে পারবে? তো কোন মেটেরিয়াল পিওর না ইমপিওর জানার জন্য প্রথম উপায় হচ্ছে, তোমার কাছে যদি একটা এক্স-রে ডিফ্রাক্টোমিটার ইনস্ট্রুমেন্ট থাকে, তুমি সঙ্গে সঙ্গে তোমার কম্পাউন্ডটা ওই ইনস্ট্রুমেন্টের সাহায্যে ডিরেক্ট জেনে যাবে ওই মেটেরিয়ালটা কতটা পিওর এবং ওর মধ্যে কতটা ইমপিউরিটি আছে। এবং অবশ্যই এক্স-রে ডিফ্রাক্টোমিটার ইনস্ট্রুমেন্টের দাম খুব প্রচুর, এবং আমাদের ল্যাবে আছে। ওকে ওকে সো instrument cost কিন্তু খুব হাই, যেটা হচ্ছে 60 lakhs minimum. And now the crystal structure and phase identification is confirmed by obviously X-ray diffractometer or X-ray diffraction analysis. And the copper nitrogen bonding and carbon double bond nitrogen carbon is also confirmed by FTI analysis. মানে তোমরা স্পেকট্রোস্কোপিক নাম শুনে থাকবে, আইআর স্পেকট্রোস্কোপির মাধ্যমে তোমরা কিন্তু অ্যানালিসিস করে জানতে পারবে আমার কম্পাউন্ডটা ঠিক তৈরি হয়েছে কিনা। এবং ফ্রম মাইক্রোস্কোপিক ইনভেস্টিগেশন, মানে ফিল্ড ইলেকট্রন স্ক্যান ইলেকট্রন মাইক্রোস্কোপ, সেখান থেকে তুমি জানতে পারবে এটা ন্যানোটিউব ফরমেশন হয়েছে কি হয়নি। Now the most interesting part of this work is growth mechanism, how these nanotubes were grown during hydrothermal treatment. এবং আমি এখানে ডিটেইলস মেকানিজম এখানে অ্যানালিসিস করে দেখিয়েছি এবং মাইক্রোস্কোপিক সাহায্যে মরফোলজিক্যাল ইভলিউশন আর অলসো ক্লিয়ারলি শোন হিয়ার। I studied the cold cathode emission characteristics of this nanotube for the development of field emission display. The turn-on voltage are from 2.0 volt to 4.0 volt per micrometer, and the field enhancement factor can be calculated from this using Fowler-Nernst model. Actually, the physical significance of field enhancement factor is that the field amplification factor or field amplifies due to the nano dimension. The estimated enhancement factor for different inter-electrode distance are found to be 1067, 1300, 1650. And finally, I studied the stability test. Means আমি কতক্ষণ টাইম ধরে আমি আমার ডিসপ্লে বা টিভিটাকে আমি ইউজ করতে পারবো, রান করতে পারবো, এবং সেটা মাই সিনথেসাইজ ন্যানোটিউব শোড দ্যাট ইট ক্যান বি ইউজড up to 200 minutes. I mean, again, I applied the argon plasma treatment on the wall of the CPC nanotube, and I have obtained the different morphology, and by varying the plasma treatment time, I can obtain the CPC nanotube, nano rod, different morphology. So the enhanced cold cathode emission behavior was observed here, and I can calculate the enhancement factor ratio beta tube by tube is 1.54, and the simulated value is 1.5. So both value will match each other. From engineering application point of view, the question arises: can I develop this CPC nanotube in large scale or practical application? এবং সাকসেসফুলি আমরা একটা ডেভেলপ করেছি নোভেল মেথড, যেখানে আমরা এই ধরনের সিউপিসি ন্যানোটিউব খুব লার্জ স্কেল অর গ্রাম স্কেলে ডেভেলপ করতে পারি। এবং রিসেন্টলি আমরা একটা পেটেন্ট ফাইল করেছি এই প্রসেসটার উপরে, এবং এখানে এই রিঅ্যাকশনটাকে আই হ্যাভ ইউজ, এবং আই হ্যাভ ইউজড এ সুটেবল ক্যাটালিস্ট। Now moving to the second part of this presentation, development of suitable anode. So I have developed the samarium and sodium coat of calcium titanate anode components by using sol gel technique. The crystal structure and purification of this nano phosphor or nano anode component are confirmed by X-ray diffraction analysis, and the particle size from microscopic investigation, it is seen that in the range of 30 to 50 nanometer. The valence state, exact valence state of calcium 2+ or samarium 3+ or titanium 4+ is confirmed by X-ray photoelectron spectroscopy technique. I have performed the photoluminescence properties of this synthesized anode component or nanophosphor with the help of spectrophotometer. And this synthesized nanophosphor showed the bright orange emission under 408 nanometer excitation. The emission is also confirmed by CI diagram, I mean color chromatography diagram. Again, I have also developed a magnesium aluminate europium lithium code of anode component. This nanophosphor also showed the bright red emission under 395 nanometer excitation. So now summary and future perspective. Already I have discussed or developed the anode component. I have also developed the cathode component, and my planning is to develop the field emission display using this cathode and anode. তোমরা বেশিরভাগ যে টিভি গুলো দেখেছো সেগুলো নরমালি হচ্ছে ফ্ল্যাট, সো আমরা ফ্লেক্সিবল টিভি যদি বানাতে চাই তাহলে আমাদের ক্যাথোড এবং অ্যানোড কম্পোনেন্ট ফ্লেক্সিবল হতে হবে। তো সেই কারণে আমরা ফ্লেক্সিবল ক্যাথোড এবং ফ্লেক্সিবল অ্যানোড বানানোর জন্য চেষ্টা করেছি এবং আমরা খুব সাকসেসফুলি উই হ্যাভ ডেভেলপড ইট। এগুলো these are the significant achievement I am not mentioning here. এগুলো রিসেন্ট আমাদের পেটেন্ট এন্ড কিছু আমি পাবলিকেশন এবং পেটেন্টস গুলো এবং ইনভেনশন ডিসক্লোজার গুলো রয়েছে। আমি একটা জাস্ট আই ওয়ান্ট টু শো এ মুভি। আচ্ছা, তোমরা বাড়িতে যে ড্রিঙ্কিং ওয়াটার খাও ওতে এখন তো বেশিরভাগ শুনে থাকবে কি কি কন্টামিনেন্টস থাকতে পারে, শুনে থাকতে পারো। আর্সেনিকের নাম শুনেছো? আর কি কি শুনে থাকতে পারো? ফ্লুরাইড। আর কি কি থাকতে পারে? আয়রন, মার্কারি। আচ্ছা, এইগুলো টেস্ট কন্টামিনেন্ট ডিটেক্ট করার জন্য কি কি ইনস্ট্রুমেন্ট তোমাদের কাছে রয়েছে, নাম শুনেছো? এই মুহূর্তে এইগুলো ডিটেক্ট করা যায় স্পেকট্রোফটোমিটার দিয়ে বা স্পেকট্রোস্কোপি টেকনিক দিয়ে বা কালারিমিটার দিয়ে। মার্কেট অ্যাভেলেবেল এই ইনস্ট্রুমেন্ট গুলো দেখবে তোমাদের বিভিন্ন ভিডিও অফিসে, গ্রাম পঞ্চায়েতের অফিসে রয়েছে এবং এর কস্ট হচ্ছে 50,000 রুপিস। আমরা প্রথম এটা ডেভেলপ করার চেষ্টা করেছি আমাদের ল্যাবে একটা পোর্টেবল ডিভাইস which can detect these contaminants, I mean fluoride, chromium, iron, using this device, and the cost of our fabricated device is only 1,500 rupees. So and in last year we have filed patent on this device. এইটা হচ্ছে পোর্টেবল ডিভাইস। এটা এবারে তুমি ডিভাইসে স্যাম্পল দিলে যেটা কোথায় পাবে তার জন্য আমরা একটা মোবাইল অ্যাপস বানিয়েছি যেখানে তোমাকে সিলেক্ট করতে হবে তুমি কোন কন্টামিনেন্ট ডিটেক্ট করতে চাও, ফ্লুরাইড, আইদার আয়রন অথবা ক্রোমিয়াম অথবা আর্সেনিক অথবা লেড অথবা মার্কারি। এর জন্য প্রথমে আমাকে তাহলে ব্ল্যাঙ্ক স্যাম্পল দিতে হবে, পিওর ড্রিঙ্কিং ওয়াটার বা ডিআইনেসড ওয়াটার বা ডিস্টিল ওয়াটার। এখানে আমি ইনস্ট্রুমেন্টে পুট করলাম এখানে, এবং এখানে আমি মোড দিলাম ব্ল্যাঙ্ক মোড। তারপর আমাকে কন্টামিনেটেড যে ওয়াটার আছে সেইটা আমি রান করলাম এবং সেখানে আমাকে ডিভাইস সঙ্গে সঙ্গে দেখিয়ে দেবে আমার কনসেন্ট্রেশন স্যাম্পেলের কত আছে, মানে ড্রিঙ্কিং ওয়াটারের মধ্যে কতটা আছে। আমরা এটা ক্রোমিয়াম দিয়ে দেখেছিলাম, তাতে কনসেন্ট্রেশন হচ্ছে 0.1 ppm। নট অনলি দ্যাট, তোমরা যে বেশিরভাগ ড্রেসগুলো ইউজ করো এখন, তোমরা যে কালারফুল ড্রেসগুলো পরো এগুলো তো টেক্সটাইল ইন্ডাস্ট্রিতে কালার করা হয় এবং এই জাতীয় যে কালারগুলো সেগুলো হচ্ছে তোমাদের ওয়েস্ট ওয়াটার হিসাবে ছেড়ে দেওয়া হয়, মানে বিভিন্ন ড্রেনেজ করা হয়। তো ওইগুলো ড্রাইড মানে ফিল্ডে গিয়ে ডিরেক্ট তুমি ওই কতটা পরিমাণ কালার ডিগ্রেড হচ্ছে বা মনিটর করা যায়। মানে ইনিশিয়ালি তোমাকে ধরো টেক্সটাইল ইন্ডাস্ট্রিতে তুমি কালার করলে কোনো একটা ড্রেস বা কোনো একটা মানে কি বলবো শার্ট, ইনিশিয়ালি আমাকে কনসেন্ট্রেশন তুমি দেখলে যে ওখানে 100% আছে। তো কন্টিনিউয়াস আমাকে কি করতে হয়, আমাদের একটা ক্যাটালিস্ট গুলো বানাতে হয়। ক্যাটালিস্ট গুলো ওখানে দিলে একটা সময় পরে ওই ড্রাই গুলো যেগুলো টেক্সটাইল কালার করার পরে যে ড্রাই আমি ছেড়ে দিই কালার গুলোকে, সেগুলোকে ডিগ্রেড হয়ে যাতে কালারলেস হয়ে আমাকে নদী নালা বা সমুদ্রে যেতে পারে, যাতে ইকোসিস্টেমে আমার কোনো প্রবলেম না হয়। তো আমরা কন্টিনিউয়াস কতটা পরিমাণ ক্যাটালিস্ট দিলে কতটা পরিমাণ আবার কালার চেঞ্জ হবে আমরা এই সিস্টেমে মেজার করতে পারি। এবং আমরা অলরেডি এই টেকনোলজিটাকে ট্রান্সফার করার চেষ্টা করছি বিভিন্ন ইন্ডাস্ট্রিতে, এবং ইন্ডাস্ট্রি কি ওরা আমাদের এই টেকনোলজিটাকে নিয়ে তারা মার্কেট ওরা বানাবে এবং আশা করি কিছু উইদিন 5 ইয়ার্স এটা মার্কেট অ্যাভেলেবল হতে পারে এই টেকনোলজিটা। থ্যাংক ইউ সো মাচ।
last speaker of this session. So all good things come to an end, so it is. The last one is, Devarshi Maharaj will give you the vote of thanks.
3 minutes. ঘড়ি দেখতে থাকো, you start watching your hand dials. I'll not take more than 2 to 3 minutes. So, as we, you heard a lot since morning, and we all rather. So now, formally, to conclude the program, it's become our responsibility on behalf of Ramakrishna Mission Vidyamandira Narendrapur to finally conclude the program and deliver the vote of thanks. So, as you know, we are habituated every day, almost all whoever spoke, they are teachers or somewhere or other they are, associated to teaching. So whenever we see these young faces before us, we automatically feel we start talking. So in this last moment, I remember one very small story, will be very, very significant to this day, this entire event of the day. That is, once in the kids' school, it's a kindergarten school, one small girl is studying in kindergarten. What happened? One teacher was teaching the girl maths, simple maths. So the problem started like this. Hey, you are given 5 apples first, and then 2 apples or 3 apples are taken away. Now, how many will remain? You see, the answer of the small girl, amongst many, was very interesting. The small girl replied, it will be 3. The teacher said, sorry, what is this? 5 is given, 3 is taken away. How can it be 3? 5 minus 3 will be, again the girl said, it will be 3. The teacher, after asking 3-4 times, got little annoyed and started scolding the girl. The kid, then the girl was naturally very upset. So after the class, what was important, another teacher, he noticed that. He called her. What happened? Why can't you tell the correct answer? 5 is given, 3 is taken away. How can it be 3? 5 minus 3 will be 2. Then what answer the girl gave was very, very interesting. He said, why? In the morning, my mom kept 1 more apple in my bag. So, she was counting that. So, when something we are going to deliver, it is very important for a teacher to understand the condition or the perspective of the student. So, since the morning, what I was observing, that all these eminent teachers and scientists, whatever, to their level best, they try to come down to the level of you people especially and try to deliver at their level best. So I thank everyone since the morning. The first was Professor Ashok Mullik. Nicely he told about this magical figures innovated by Ramanujan. Then our heartfelt thanks to Professor Indranil Manna. It's a very beautiful culmination of science, technology and engineering. We extend our thanks to Professor Tanushree Shaha Dasgupta, who spoke about the materials of the nanoscale measurement, and Professor Vikramjit Basu also. Our sincere thanks, who spoke nicely about the stem cell, and finally Professor Rahul Banerjee. So Professor Rahul Banerjee said, whoever wants, if any one of you wants to further communicate him, you can take the number from our UKG sir, Professor Uttam Ghorai. We have his number. If any one of you want to contact him over mail or over phone, you can get the number from Professor Ghorai. So he also nicely spoke about metallic organic framework. It's a beautiful presentation. And we also thank Professor Uttam Ghorai, who is the convener of this program. Last but not the least, our most sincere thanks goes to this entire audience, that is you people. You are you played the most pivotal role to make this entire endeavor very successful. We thank you very, very much, and the teacher or the mentors who accompanied this entire team. We thank all of them. And of course,
our very, revered teacher who conducted the program since morning, Viprodash Bhattacharya. We convey our very, very heartfelt thanks to him for conducting the program very beautifully. It is, it's an auditory delight to hear his communication. And of course, the technical staff, Subrata, he was very much known to us in that name. He was our staff of Lok Shiksha Parishad and all other staff members who worked behind the screen. Thank you all. And the last announcement is regarding the certificate. This participation certificate for all our school Vidyalaya boys, they will get certificate. It is already given. It is handed over to Shandipan Maharaj. He will give you. And to the other schools, the participants who joined from other institutions, the teacher, the representative teacher or the mentor, he is requested to collect the certificate for the entire team from our registration counter. Thank you once again. Thank you all.